The universe is marvelous. Just look at the sky. Huge planets, bright stars, vast galaxies, massive clusters. It just fills us with tremendous amazement. In the last century, our exploration of the cosmos has reached unprecedented depths. From the first echoes of the Big Bang to the accelerating expansion of space, from dark matter and dark energy to ripples in space-time itself. Yet, with every answer, deeper questions have arisen. How far are we in understanding our universe? What lies at its beginning? Are there limits to knowledge, observation, and even comprehension? Is the astonishing order of the cosmos merely accidental? Or does its beauty, fine-tuning, and mathematical elegance point toward a deeper intelligence and purpose, as some of the greatest scientific minds have reflected across generations? To explore these profound questions, Bhaktivedanta Institute invites you to an extraordinary voyage through our cosmos, where some of the world's most brilliant scientific minds will share their insights and discoveries, including Andre D. Linda from Stanford University, John H. Schwartz, theoretical physicist, Caltech, USA, Wendy L. Friedman from the University of Chicago, Ofer Lahav from University College London, Avi Loeb, Harvard University, USA, Pankaj S. Joshi International Center for Space and Cosmology, India, and many more leading thinkers from across the globe. This is a space for rigorous science, open inquiry, and meaningful dialogue, where curiosity meets humility. Welcome back to your own astonishing home, the universe.
Good evening, one and all. Thank you for joining back. Every day is a new beginning, new experience, fresh curiosities, and knowledge updations. Hearty welcome to all of the guests, dignitaries, speakers, faculty members, and all our participants for joining us today from across the country and all over the globe. For the Golden Jubilee lectures on Voyage through the Cosmos, delving into history, models, theories, latest images, and foundational issues in understanding the universe. To a new beginning, and which is full of enriching talks and constructive and collaborative interactions that enhance our knowledge. My name is Shravan, and it is my privilege to be your host for today's program. Today is day 4 of the lecture series, which began on 16th of March, that is Monday, and will continue till 22nd of March, that is Sunday, in online mode, bringing together distinguished scientists, scholars, and brilliant thinkers around the world. This lecture series is organized by Bhaktivedanta Institute, Kolkata, as part of its Golden Jubilee celebrations, marking 50 years of dedicated service to the humanity. The timings of the lectures are from 5 p.m. to 8 p.m. Indian Standard Time from Monday to Friday, that is till tomorrow, and 10 a.m. to 1 p.m. on weekends, that is Saturday and Sunday, again Indian Standard Time. So before we start with today's lectures, let me go through today's schedule briefly. The first talk will be delivered by Professor Louis Marmet, who is among us from York University, Toronto. He will be speaking on an interesting topic, an optical illusion at the crossroads of cosmological models. The second talk will be delivered by Professor Livio, formerly from the Space Telescope Science Institute. He will speak on the intriguing topic, Is Earth Exceptional? The third and final talk will be delivered by Professor Tejinder Singh. He is formerly from TIFR Mumbai and visiting professor of IUCAA. He will be speaking on the topic Quantum Theory, Gravity, and the Cosmos. So Before we proceed with the first talk, I would like to request all the participants to please make a note of our procedure. All of you are aware with this, but once again, we are reminding that in order to ask the questions, either during the session or at the end of the session, please do scan the QR code that is displayed on the screen, or a Google form link will be shared over the chat for asking the questions. Please do follow the chat box as well for asking the questions. So it is my great privilege to introduce our distinguished speaker of today's first talk, Professor Louis. Louis Marmet is an adjunct professor of physics at York University in Toronto. He studies light matter interactions and their importance in our interpretation of astrophysical phenomena. Marmet has obtained his PhD in physics from the University of Toronto with specialization in experimental quantum optics. As an Alexander von Humboldt Fellow at the Ludwig Maximilian University of Munich, he conducted research on quantum chaos in atomic systems. His career at the National Research Council Canada focused on high precision atomic clocks and laser cooling of atoms to microkelvin temperatures. Marmet is currently collaborating with a group of York University on the experiment that uses an atom interferometer sensitive even to detect laser heating from a single photon interaction. Professor Marmet's passion for physics appeared at an early stage, inspired by his father, who was also a physicist and introduced him to the principles of measurement, inquiry, and profound desire to understand the world. His interests led him to a broad range of activities that include amateur astronomy, photography, mathematical modeling, philosophy of science, and astrophysics. These diverse skills are key for perceiving nature with a distinct clarity, as he recognizes that illusions pose a constant challenge to knowledge. This unique lens is especially important in cosmology, a discipline at the intersection of science and philosophy. Marmet believes his perspectives can offer a fresh understanding of the universe we inhabit. Since 2018, he has been facilitating a discussion group focused on cosmology, fostering dialogue and explorations of these themes. So I request Professor Louis to take over the session with this brief intro. Sir, please hand over the session and deliver your talk.
Thank you very much, Sravan. Let me share my screen here. And
Yes,
start
able to
the
see.
show. This looks good.
Perfect to go.
Yes, thank you very much. I wish to thank the Bhaktivedanta Institute for inviting me to speak today. As you saw, my background is in experimental quantum optics, and so my view of the universe is very based on what we see. And I'll start this talk with a well-known parable of the four blind men and the elephant. Here on this slide, we see four astronomers who are trying to measure the Hubble constant, the constant that gives us an idea of how fast the universe is expanding. And there are many techniques that are used to determine this constant. And unfortunately, when you get the values with these different techniques, the numbers disagree. And the difference is quite large between the smallest and the largest. And as you've seen in previous talk already, this is called the Hubble tension, and it's a fairly serious problem in cosmology, because the expansion of the universe is fundamental to our cosmology today, Big Bang cosmology. And so I think here that we have a case that is very similar to the parable of the blind men, is that there's something we don't see, and that's why we don't get the same numbers for these different techniques, outside, of course, of experimental difficulties. These are very difficult measurements. So through this talk, yes?
Yeah, if possible, you can hide your control panel.
Let's
visible
see.
on the screen.
Is that, no? How's that? I'll put it down here. Throughout this talk, my claim will be that without optics theory, our interpretations of what we see are rather blind. There are many questions to discuss in cosmology. Of course, too much to talk about in a 45-minute talk. Here, I'll limit this discussion to a very few simple questions concerning the approach we have to cosmology and the scientific method in cosmology, and finally, the interpretation of observations, which are not unique. There may be many ways to interpret what we see. So to simplify things, I use two categories. First of all, there's an empirical approach to science, which is to observations or knowledge, which is usually done through the scientific method. And there's the interpretive method, which is more from personal experiences and observations and spiritual beliefs. So we can separate different cosmologies that exist with these criteria. And then on this axis here, I split the different cosmologies depending on whether they claim the space is expanding or non-expansion of space. So in this talk here, I will mainly focus on the empirical cosmologies, and I'll take lambda CDM, the most recent version of the Big Bang Theory, as an example. And on the non-expansion side, I'll discuss the static plasma cosmology. Tim Eastman discussed this a bit yesterday, so this will be a continuation of that discussion. Now, the scientific method in cosmology is a little bit hard to apply because some of the ideal assumptions made for by the scientific method cannot be applied. So, for example, when our theories are supposed to be testable, but it's very difficult or impossible to get feedback from what we do. We can do experiments, but we don't have experiments where we can, for example, spin a galaxy in the other direction and see what happens. Also, when we see strange phenomena, it's very difficult to get independent confirmation of what we see because we don't have access to all the stars and the galaxies to change the initial conditions. And so while most of the cosmology uses the scientific method, some parts of it are rather difficult or impossible to do. George Ellis also discussed this yesterday in great length. So I'm going to move over to our observations. Now, our observations with the fancy telescopes we have are an extension of our senses. And we understand this part, I think, very well. I was discussing with a philosopher some years ago. He was telling me, well, the James Webb telescope is a new instrument. How do you know it works? And I showed him this figure here. I said, well, this telescope is actually a Cassegrain telescope, which was invented 350 years ago, and we understand it very well. And actually, I find it amazing that the diagram put up by NASA is very similar to the diagram that Cassegrain had in his book in 1672. So As far as I'm concerned, like as for an experimental physicist, our observations, our instruments are just an extension of our senses, and this is very well understood. Where it gets more difficult is when we look at things that are extremely far away. So this is the galaxy here, MOM Z14, which is the farthest confirmed galaxy we have so far. This is so far away that there could be optical illusions on the light that's reaching us, and an objective interpretation of what we see becomes much more difficult. So let's start with the measurement of the Hubble constant. Almost 100 years ago now, Hubble started looking at photographic plates and analyzed galaxies we were seeing. And so what we know for sure with our instruments are the light we're getting from it, and we can analyze its spectrum, for example, its intensity. We know the angular size of the objects we see. We can see galaxies somewhat larger, appear larger on the photographic plate. And for objects that have that are transients, so we can measure the time duration of these objects, like supernovae, pulsars, all these things. These things are measured, and we understand very well what we see. When it comes to interpretations, though, this becomes more difficult because then we have a choice of understanding what we see. And for example, a redshift, there are a few different ways to interpret what the redshift means. In Hubble's time astronomy, the interpretation was that redshift was caused by a velocity, a Doppler effect that reflects a velocity. And for example, the luminous flux, also how bright the object is, we see that as meaning distance. So the fainter the object is, the farther away it is from us, which is our common experience. So Hubble plotted this relationship that he saw with many galaxies, and he saw that when the object is further distant away, the redshift becomes larger, which was a very important discovery, actually. And they tried to explain it by interpreting what redshift means and what distance means. And at the time, of course, Einstein had just come up with his relativity, general relativity theory. And so this was immediately applied to try to understand what Hubble had seen. And so the interpretation is that space expands, and the expansion increases distance to those galaxies we're looking at with time, and therefore this is a velocity that produces a Doppler effect and dimming of the galaxies. They're getting fainter and fainter because of the velocity, the recession velocity of these galaxies. And since then, there's been many observations to try to see if this made sense. I'm going to just give you one example of observational evidence. I think this is a very good, maybe the best result we have. So this plot here shows the luminosity distance, that is the distance we get from the luminosity of an object, as a function of redshift. And so the bigger the redshift, the distance increases. This is a measurement of supernova distance. And as you can see, this is a theoretical equation from a solution of Einstein's equation. And by adjusting various parameters, so there's the Hubble constant here again, but also the amount of matter, the density of matter in the universe, its curvature, and of course, a dark energy lambda constant. We can fit these data extremely well, as shown by the black line here. This is one of the many observational evidence that we have that our description of the universe is correct. Now, there are many more, but I think the previous speakers and the speakers tomorrow also later will discuss all this. So I'll just list the strength of the expansionary cosmology. And of course, those that are important are that we have an agreement with the redshift distance relation. So that's the curve I just showed. It describes the cosmic microwave background very well. It explains the nucleosynthesis of light elements in the cosmos, and the evolution of structure, galaxies, filaments, and so on, is also modeled fairly well. Of course, there's consistency with general relativity, since it's derived from relativity, and it's the best model we have so far. Now, on the other hand, there are weaknesses as well. Since the interpretation implies a Big Bang, there is a period of very dense energy at the beginning of the universe, and at these high energies, the cosmic laws are not known very well, or not at all. And another problem is that there are many coincidences that appear. We need fine-tuning, and some ad hoc assumptions must be made to make all this work. And with time, like since the history in the last century, essentially, there has always been issues showing up and tensions, and the cosmology we had has always been subject to revisions. Now, for some people, this is just an indication of how science progresses, but this is different actually from, for example, if you take quantum mechanics, which also is about 100 years old, the equation written down by Schrödinger hasn't changed since then, while in cosmology, the equation describing the expansion of the universe, for example, has changed drastically. So it seems the model is still, after 100 years, a bit on shaky grounds. So I'll break my talk in two, showing this photo here, just to show that, to explain what I see when I look at this. Of course, we see all these clumps of light, which we know are galaxies, and they're formed by gravity. Gravity pulls matter and creates all these nice structures. But in addition to this, what I see in there is that this light we see is emitted by hot plasmas. They're the stars that give the light off. And the third thing I see as a specialist in optics is that, well, we see light. And so this light has traveled extremely long distances to reach us, and might have been affected by this long journey toward our telescopes. So when you think about cosmology, of course, gravity is very important. But as Tim Eastman said yesterday, plasmas have a very important role because they're not fully shielded, they're not neutral. And I wrote here some example of the Boltzmann transport equation and Maxwell equation. And I describe this interaction here of the plasma with currents and so on, as fields tells us tells charges how to move, and charges tell fields how to curl. Sort of to repeat John Wheeler when he was talking about gravity. Now, my specialty is quantum optics, and of course, the important equation here, Schrödinger's equation in quantum electrodynamics, describes how light carries energy and momentum between these charges of the plasma. And this is also a very strong interaction at the scale of the universe, comparable to what plasmas and gravity are doing. And in some cases, actually, it is stronger. So let's go back to Hubble, and when he's not with Einstein looking through the telescope, he also had some doubts about the interpretation of redshift, or he knew that there was another possibility. So in 1932, Macmillan wrote that the interpretation in terms of light quanta, quantum mechanics, is much less disturbing. And even Hubble was trying to find a way to explain the redshift in a way that does not involve actual motion. That is, no expansion. The effect is on the light that's coming to us, that's being reddened. So Fritz Zwicky, everybody knows him for his hypothesis of dark matter, also suggested that photons lose energy as they travel. He didn't know exactly how, but of course, some properties were very important to explain what we see. Most critically, the effect had to be wavelength independent. There had to be no diffusion of light. Of course, otherwise we wouldn't see all these galaxies at large distances. There had to be no absorption of light. And the process would follow essentially a reduction of energy or intensity that would be proportional to some cross-section and the number of interactions on the path to between the galaxy and us. So the interpretation suggested by Zwicky was that a spectral interaction produces a redshift as light propagates through the intergalactic medium. Now the question is, how does that happen? How can we explain this theoretically? And I don't want you to read all these papers here, but many people had many ideas and published all these ideas since 1931. So this is a sample of publications in the last 100 years. And if you look at these papers, about 33% of them assume a redshift mechanism. They don't know what it is, but derive their implication in terms of cosmology. Another 33% propose some new cosmic physics to fit observations, but unfortunately, this doesn't turn out as being measured or observed on Earth in the laboratory. And so the theory never gets accepted. And finally, there are many people who publish papers that use established physics, but they ignore some mistakes that are made, and their predictions are not very useful. So given the large number of papers, and this was kind of lumped into one category called tired light. This is a name actually proposed by Zwicky, but it didn't take long for other scientists to refute these theories. Ned Wright actually refuted most of these theories, and there were even experimental tests done to try to see if we could see redshift in electrons caused by electrons, and but there was a null result obtained in 1936. Actually, it was fairly early. So, as this webpage says, there's a blurring of distant objects. That is, if you have a blue photon coming in that goes through a medium, and you assume energy conservation, momentum conservation, causality, it is impossible to produce a red photon, a redshifted photon from it that travels in the same direction. And this was argued actually fairly early too, in 1953, by Atkinson, who discussed this in more detail. So it would seem that since there's no physical mechanism that can produce this, finding a tired light theory that would explain the cosmological redshift is a lost cause. And this is impossible as it is now. And this is the common consensus in astrophysics today. Now, all hope is not lost. Quantum optics has, there's been a lot of developments in optics science since Atkinson's argument in 1953. And one effect that is very interesting, that was actually predicted in 1933, is the Kapitsa-Dirac effect. And it was predicted that electrons should also be diffracted by standing light wave. And this is a very small effect. It was only actually experimentally measured in 2001, almost 70 years after its prediction. But Kapitsa and Dirac were right. Light can interact with electrons and produce an exchange of momentum between the light and the electrons. So I'm going to spend a bit more time here on this slide just to show how the effect works. Essentially, to get the standing wave, we need two beams. One photon, a blue photon coming in, and one red photon coming in. And they interact with an electron at rest. During this interference, because they interfere, they give the electron a momentum kick, which pushes the electron up on this diagram. And the photon is scattered into the initial red beam by a stimulated emission process. So that's again Einstein coming here to help us understand what's going on. Because if it's a stimulated emission process, that means the red photon is going exactly in the same direction as the initial red photon. And so here you see that we have initially a blue photon and a red photon. And at the exit of this experiment, we have two red photons and an electron with a little bit of momentum that's recoiling. Now, if we put this in the context of a bit more realistic spectrum of light, we see that we can have light with a spectrum that has two blue photons and one red photon interacting with another beam that is also bluer, two blue photons, one red photon. Then once you go through interactions with a few electrons, what you get in the end result is that the spectrum of this beam has been shifted to the red. Now there are two red photons. Same for this beam here. Now the properties of this are very good in the sense that it's a Doppler recoil redshift. The electron recoils and emits the red photons. So it has the properties that the redshift is wavelength independent. And because it is a recoil, it is really a velocity of the electrons that will stretch time-dependent light pulses or any pulse emitted by a transient. So the second property is stimulated emission, because it is this effect that's implied in the electron-induced redshift. The beams don't change direction. That is, the initial beam coming in this way exits here in the same direction. Stimulated emission is well known for its operation in lasers, where you have very collimated beams. And that's because there's no scattering that changes the direction. There's no diffusion of the direction of the beams. Because the process is an interference effect, it's linear in intensity, and this becomes important for the low intensities of intergalactic space, where light is not very bright, there's some momentum diffusion. That is, after the process, the electrons are heated. They have acquired momentum and therefore have a higher temperature. And of course, the process is proportional to the electron density. The more electron density you have, the higher, the more often the process happens. And so this is described as a cross-section, sigma, and the average number of electrons involved in the interaction. So the Kapitsa-Dirac effect is actually an effect that makes this type of redshift possible. You have beams entering a black box, beam exiting a black box with a redshift on the spectrum. So let's look now at observational evidence for this. Since there were papers published from early on that assume that if there is such a tired light redshift, they derived a cosmology. In the 1930s, Nernst and Macmillan derived what's called a Nernst-Macmillan cosmology, where they showed what the equations would be for different distance measures. And so according to this is simply a solution, actually, of the Beer-Lambert equation. The distance depends on the logarithmic function of 1 plus z redshift. And in a recent paper, 2022, this graph was published, which shows all the black dots here are diameters measured for different galaxies. And even the red dots here show diameters of galaxies measured by the Webb Space Telescope. And you see that this follows the line predicted almost 100 years ago as the angular distance measurement. Now, you'll notice that the lambda CDM prediction would imply that the diameter, the apparent diameter, would actually increase at very large redshift, and it disagrees with observations. So what's happening here? And to explain that, the standard cosmology says, well, our galaxies don't have a constant size. They're not all 10 kiloparsec in size. There's evolution of their diameter because we're getting near the Big Bang here at these distances. And so galaxies were not this diameter, but much smaller just after the Big Bang. And that's why we see them below the predicted line of lambda CDM. Here, the static cosmology does not have that option. Galaxies, there's no evolution of galaxy, pardon me, in static cosmology because essentially there's no Big Bang to trigger all these galaxies to start forming at the same time. And so while each galaxy evolves on its own, there's no common starting point that has triggered and synchronized all this evolution. And so with this very simple equation, we fit data very well. Number two, there was this test that was derived or invented in 1930 by Richard Tolman. And he said, well, what we could do is measure the surface brightness, excuse me, of galaxies to see if the universe is really expanding or not. And in his paper, he concludes that if the Tolman signal is 1, then that shows there's no expansion. If the Tolman signal is 4, then that shows there is expansion. Now, these are actual fairly recent results. And what is seen is that there is actually no change of the signal as a function of redshift. and so the surface brightness is constant, which means a Tolman signal of 1, which shows there's non-expansion. Again, this is given by a very simple formula, and show on this graph what would be expected if the universe was expanding, and it's of course very different. But again, lambda CDM claims that galaxies are evolving, and therefore they are actually brighter. Brighter galaxies is down on this graph. They are actually brighter than expected. But this is still not very well understood. As they say here, a large portion is left unexplained of this evolution. This is the same graph I showed earlier with the supernova distance as a function of redshift. In this case, the static universe, the static cosmology equation agrees. It's again the same equation with just a factor here, 1 plus z, because of the stretching of the light curve and, of course, the redshift. And so here the agreement is extremely good. It actually covers the black line that's underneath here. And so this constitutes observational evidence number 3 for the luminosity distance. All that is done with this very simple equation that essentially has only one parameter, the electron density in space on the path between the galaxy, the supernova, and us. Now, it would be interesting if we could actually independently measure this number density, because, I mean, while this effect might exist, if its amplitude, like if it's very small, then it would not explain the cosmological redshift as an electron redshift. And we've been lucky in the last 20 years. There's been a discovery of fast radio bursts. So for those of you who don't know what it is we've detected some very short radio pulses with radio telescopes that come from very distant explosions. The model is not quite understood yet, that happen in very distant galaxies. And starting in 2017, these explosions were located very precisely and associated with a host galaxy. So while we could measure the fast radio burst with our telescopes, and the dispersion of the radio waves, which is proportional actually to the number of electrons, we could also measure its redshift because we could take the spectrum of the galaxy. So two processes now are happening in parallel. There's this radio pulse traveling through intergalactic space, and from plasma physics, we know that the pulse is dispersed, and it's calculated easily with this equation here that is, it's essentially proportional to the number of electrons that are interacting with the pulse. Now, the electron redshift for the static cosmology depends exactly on the same quantity, the number of electrons that have interacted. And therefore, because these two quantities are the same, we can just simply take the dispersion measure and plug it in this equation, and we get this very simple relationship between dispersion measured, that's measured with radio telescope, and the redshift, with this proportionally constant here, which is the redshift cross-section, again, given by theory as being this value. So by 2025, last year, there were over 120 fast radio bursts that were localized. So we have, for each radio burst, here we have their redshift, and then we have their dispersion measure, and there's a host contribution, that is a host galaxy also causes a little bit of dispersion, which is added on top. But this means that we should expect all measurements to be above this line here, and essentially no measurements below, because that's what's contributed by the intergalactic medium. And so the equation, the simple equation that I showed on a previous slide is plotted here. That's this line. And the fit is, the match is very good. There's no adjustable parameter. I just use a calculated cross-section. And it confirms that this value is correct to about 5% uncertainty. So this observational evidence has very profound implications, because this means that the electron redshift is strong enough to contribute to account for 100% of the cosmological redshift. And therefore, if this is what's happening, what's redshifting the galaxies, the light of the galaxies, then there is no room left for space expansion. I showed you earlier how the process gives a momentum kick to the electrons and therefore heats them, increases their temperature. And there's been a problem in solar physics that is still unsolved. And the question is, why is the solar corona this hot? Now, solar physicists have calculated different effects. There are magnetic lines crossing and all sorts of alpha waves propagating through the solar corona that gives them some heat. But when they add all these effects, it still does not give enough energy to bring the solar corona to a 3 megakelvin temperature. But if you include also the light interacting with the electrons of the solar corona, then you can see that it brings the temperature to 3 million Kelvin. The same thing is visible here in galaxy clusters, where they've looked at the energy in the plasma that's in the middle of all these galaxies. And they find that the thermal energy in the core is about 10 times more than gravity alone should produce. So gravity does produce heating of this plasma. And my claim here, of course, is that it's, again, the redshift process, the electron-photon interaction, that provides the rest of the energy to bring these, the plasma in the galactic clusters to such a high temperature. So now here I'm getting into a bit more ahead of myself, in the sense that the theory to understand this is not derived yet. This is future work. But I've plotted on this graph here, which shows the temperature of the plasma as a function of the density. I took the original image and added the intra-cluster medium. That's the previous slide. That's what I show on a previous slide. And there's another plasma that's even has even a lower density, and it's the intergalactic medium. And it should be at a very high temperature, essentially because there are no collisions to dissipate the heat. And I show this here as this familiar diagram, which represents the microwave background, but at a temperature of 6 billion Kelvin. Now, the reason we don't see it at 6 billion Kelvin, we only see it at 2.7 Kelvin, is that electrons have an extremely low emissivity. The interaction is very rare between a photon and an electron. And this is what I write here. Compton scattering happens only, the mean free path is about 40 trillion light years. So it's a very small emissivity. And so while the plasma itself is very hot, the radiation associated with it is very cold. It would be down here on this graph. So this is research in progress, but the plasma is cooled by pair production. It's heated by redshift interactions, of course, cooled by pair productions, nuclear reactions. There's a cycle between the redshift of the microwave background and the blue shift caused by heating from Compton scattering. That's called the Sunyaev-Zeldovich effect. And to achieve the black body spectrum, there needs to be multiple Compton scatterings. What's important here is that this means that the universe must be much older than 40 trillion years so that we can achieve this black body radiation spectrum. And then in a universe that's that old, this gives a lot of time for elements to form. And not only the light elements are formed, well, the light elements are formed in the stars, and with that amount of time, they can reach the proportions that we measure today. An interesting thing is that this becomes comparable to the 311 trillion years that I read, which is calculated age of Brahma. So for some reason, this number here is now very much in agreement with what we get from just calculating Compton scattering events in the low density medium. One last thing is experimental evidence. I like this picture because this is a paper on a free electron lasers where they use a blue laser. They describe it as blue laser, but at the exit here comes out some coherent emission, which is redshifted. And of course, they benefit from the large density of electrons in the free electron laser. Now, there's a caveat to this, is that this is not exactly the same process as what's happening in space. They essentially had to use nonlinear effects to be able to see the signal, but it shows that it's possible to get a redshift in electrons from an initial light, and it's coherent. That is, it's propagating exactly in the same direction. I won't have time to go over this. There's an experiment that I plan to use at York University to try to measure some aspect of the redshift in electrons. Here, though, it's going to be done with atoms. And so I'll finish by discussing the static cosmology, its strength. It's based on known physics. It can be understood with the physics we've already discovered in the lab. It has the same evidence observations, that is, the redshift distance relations. The cosmic microwave background can be understood, as I've discussed, light elements and evolution structure. I didn't have time to discuss this consistency with relativity. This interaction with the electrons produces a pressure, which would be described as a lambda term in the equation. But it's made predictions too. It's not only that we fit the distance, it's actually this was predicted almost 100 years ago based on the redshift distance equation. It predicted that a heating of solar corona and interstellar plasma, the cross-section, the calculated cross-section is confirmed experimentally. And actually, what I'm working on now is a relationship between the Hubble constant and the temperature of the CMB. And I won't disclose what number I'm getting, but it's very close to one of the 4 measurements I showed earlier. All this without antimatter, without coincidences, just straight quantum optics. Weaknesses, they're not at the physics level, they're more at the procedure level. We need to have general relativity, plasma physics, and quantum optics all at once, interdisciplinary knowledge is essential. The infrastructure is still in development, and so some hypotheses must be accepted temporarily until we have a better description. Quantum optics and plasma physics are frameworks. They don't tell us what the cosmology is, so this is still in development. And of course, there are some questions that are asked all the time that are not, that are the limit of science. And so there are things we cannot know with science. And I think these boundaries have to be acknowledged with humility. So I'm going to quote here Max Planck's. I'm sure you've all read this. I'm not trying to convince people that this effect is real. I'm just trying to expose the new generation to this possibility so that you're familiar with it. And when you read papers, you think, this could also be a tire light effect in electrons. And hopefully by becoming more familiar with it, there'll be more people working in this field and to study its possibilities. So I'm going to leave you with this. Thank you very much.
Yeah, thank you, Professor, for your brilliant and truly inspiring lecture. I would like to express my sincere gratitude for sharing such profound insights. I hope this talk has enriched the knowledge of many of the participants, especially the serious researchers into fundamental cosmology and also quantum optics. So we understand that there is so much to explore at fundamental and foundational level. It has opened doors to budding researchers to explore more. Thank you once again, sir, for such a remarkable lecture. I hope this talk has lit up many young minds with interesting questions as well. So if time permits, we'll try to take 3 or 4 questions. Before going to the questions, let me remind once again the process of asking the questions is by scanning the QR code that is shown on the screen, and also a Google Form link is shared over the chat. So please do use that as well. First question, please. This question is by Dr. Bharat Pandey from Government PG College, Ranikhet from India. He is asking, sir, is it possible that what we perceive as the structure and evolution of the universe is not an absolute reality, but an optical illusion, emerging from the assumptions embedded in our cosmological models?
Yes, thank you for the question. I think it is. I mean, this is a question that's beyond science, really. What the actual universe, like the absolute reality is, I think we don't know, and I'm not sure the scientific method can actually let us know what this reality is. All we do is to observe correlations and describe them with the best way we can with mathematics. So we get an understanding of these different correlations between many observations we do. But the absolute reality behind this is not accessible, I believe, with the scientific method.
Thank you, sir. Thank you. And we have next question on screen, please. It is by Ritvik. Sir, can you give examples where we observe blue shifts in observational astronomy? So redshift is quite common.
Yes, there are actually, when we look at galaxies that are not too far, their proper motion is actually large enough, and some of them are moving towards us, and there's a blue shift. I think there are over 1,000 galaxies that show a blue shift. So this shows that The Doppler effect from motion of the galaxies is also valid, of course. There is real motion of individual galaxies. But as we get far away, then the electron redshift becomes dominant, and this blue shift is not visible anymore because it's been compensated by the huge redshift at large distances.
Thank you, sir. It is very much interesting to know. Can we have next question, please? It is again by Dr. Bharat Pandey from Uttarakhand, India. Sir, does the Kapitsa-Dirac effect extend Einstein's relativity into the quantum domain by making photon properties interaction dependent?
No, the Kapitsa-Dirac effect is at very low energies for like normal light or so on. You could say 2 or 3 electron volts, let's say, or less. It's such at a low energy that in terms of dynamics, the classical physics is adequate enough. And so Einstein's relativity does not really enter into this effect. It's a quantum effect, essentially, with stimulated emission. But general relativity does not really enter because the energies are too small for these photon interactions.
Okay. I hope that answered the question. Yes, can we have next question, sir? We can have 3 or more questions if you are fine with it. Yes, this question is by Kumar Ravi from Swami Vivekananda University, West Bengal, India. In one of your slides, you showed a plot depicting angular size versus redshift. The redshift range extended to about z greater than or equals to 10. Could you clarify if that is observationally supported? I was under the impression that current observational data reach up to around z approximate to 8.2 from GRBs. Is the higher redshift data based on 2022 paper you cited?
That's right. Yeah, gamma ray bursts, I think, reach a redshift of about 8.2, although the redshift of those is much more difficult to determine. But the data I showed is up to redshift 14 and even further. So the most distant galaxy that has been confirmed with a spectroscopic redshift, that is, we see the actual spectral lines, is the photo I showed at redshift 14, that equals 14. And there are many more galaxies that have been observed by the Webb telescope at redshifts up to about 20, actually. But this is only from photometric measurements. So you look at the color of the galaxy and you sort of guess very inaccurately what its redshift is. So the data points that I showed on that graph are actually from the paper. They are actual measurements, and some are certain to redshift 14. And those that are not spectroscopically confirmed, still we have a large number of them, and so statistically we can see from the color of the galaxies that these are galaxies that are extremely far away, and obey the statistics that follows the line predicted by in a static cosmology.
Yeah, thank you, sir. Thank you. Can we take 2 more questions?
Sure.
Yeah. Yes. So next question is from Professor Tejinder Singh. He is our next speaker as well. He is from Tata Institute of Fundamental Research, India. So are there observations which static cosmology explains better than expanding cosmology, or vice versa? Is static cosmology falsifiable?
Yes. So I think the 2 graphs showing the distance and the surface brightness, so the Tolman test, I think those explain better than expanding cosmology. There are still a lot of observations that are interpreted as an expanding cosmology that match data extremely well. I cannot explain them yet because I haven't developed a theory, or nobody has developed the tools to analyze this and understand what's happening in terms of cosmology. And so when we develop this tool, that is, we derive the consequences of a static cosmology, we'll see what the results are. Of course, if they disagree, that would be a way to falsify the static cosmology. So a lot of more work is needed still.
Definitely, sir. Yeah, thank you. Last question for this talk. Can we have it on screen, please? Yes, this is by Dr. Ravi Sharma. He is from Nuclear and Particles and NASA Apollo awardee. He is from California. So his question is, in addition to E-photon interaction, what are relative strengths of other interactions such as EW and strong interactions?
At this point, I've looked at interactions with visible light or infrared or microwave light, and so these are all below even the rest mass of the electron, 500 keV, and so all these effects are very classical, let's say, and so now. We know, of course, we detect very high energy photons in space, and that are way above the mass of the electron, the rest mass of the electron, and possibly then interactions such through the electroweak interaction, for example, they possibly would have some effect, but that's actually not my specialty, and so. If you're a specialist in high energy physics, of course, this effect, some effect may be equivalent to the Kapitsa direct effect, but with higher energy interactions, I think would be worth looking into, because there are a lot of things that are unexplained actually in terms of high energy radiation that's coming to us in space. There was this gamma ray. There was, I forget what the energy was, but its momentum was the equivalent of the momentum of a tennis ball, I think, that was detected. This is certainly not what I'm calculating. This is way beyond what the equations I have can understand. So this is, yeah, really the domain of high energy physics. And but I don't have any knowledge so far or idea actually what would happen. But this is certainly a possibility, and it's worth studying, I believe.
Thank you, sir. Thank you. And yes, there is a lot more to explore, and we are still learning. Yes, thank you for addressing these questions with such wonderful insights. We still have many more questions from the audience, but due to limited time, we would like to conclude here with your permission. So on behalf of
Yes, thank you very much.
Thank you, sir.
Thank you very much. It's a pleasure.
And all the audience, I would like to once again express our sincere gratitude to you for sharing your insightful talk, which has opened up many questions among us. Hope our researchers who have joined will take a serious note of that and try to explore those questions and enhance their knowledgeability. And we would like to see you more often and know more when our time permits, sir. Thank you. Thank you once again.
Thank you very much. It'd be a pleasure to talk with you again.
Thank you, sir. Thank you. So moving on with today's schedule, we have our next speaker, Professor Mario Livio, with us. We will be speaking on an interesting topic titled, "Is Earth Exceptional?" So in one sense, habitable for us. So let me take a moment to remind the participants about the Q&A session pattern that we are following. So You are all well aware of this. You have to scan the QR code that is shown on the screen, or Google Form link will be shared over chat. So you can ask the question during and even after the talk is finished. So let me take the privilege of introducing today's speaker. Professor Mario Livio is a distinguished astrophysicist and best-selling author, formerly a senior astrophysicist at the Space Telescope Science Institute, the Scientific Operations Center for the Hubble Space Telescope. His scientific research has profound seminal contributions to the theory of accretion disks, binary star evolution, type 1a supernova, and the search for the life in the universe. Livio's theoretical models have deepened humanity's understanding of how compact objects like white dwarfs and black holes interact with their environments to produce the most energetic events in the cosmos and the search for extraterrestrial life. Beyond his technical achievements, Livio is a globally recognized intellectual who bridges the gap between hard science, mathematics, and philosophy. Through influential works such as The Golden Ratio and The Brilliant Blunders, he explores the epistemic nature of discovery and the unreasonable effectiveness of mathematics in describing reality. A fellow of the American Association for the Advancement of Science, Livio combines rigorous theoretical astrophysics with a profound capacity to articulate the beauty and complexity of the universe in a simple language. So with this brief introduction, I would like to invite Professor Mario to deliver his lecture. Just to let all of you know that Mario is also a regular contributor to our Institute's foundational quest for knowing the absolute truth. Sir, I request you to please take over the session and deliver your talk.
Thank you very much. Can you hear me?
Yes, sir. Very much clear.
Okay. And you see the slide?
We are at 2.
Do you see my slide on your screen?
No, sir, not yet.
Oh, no?
We have not shared yet.
Wait. I thought it was supposed to be there. Do you see me?
Yes, sir. Your video is on and the audio is also very clear.
Yes, but why don't you see the slide? I don't exactly understand.
Maybe you can share it once again.
Do you see me now?
Yeah, you are visible, sir.
Okay.
Yes, sir. Now we are able to see the screen.
Okay, now you see the full screen?
Yes, sir.
Okay,
It
good.
We are good
You see the slide that says, is Earth exceptional, right?
Yes, sir.
Okay, good. Thank you. Sorry about the little
Thank you.
thing. Okay. Okay, is Earth exceptional is the topic of my talk, and it is based on this book, Is Earth Exceptional? The Quest for Cosmic Life. The book was written in collaboration with the Nobel laureate Jack Szostak. So here is me trying to put together a whole galaxy, and here is Jack, who is trying to create life in his lab. We deal with two important questions, and these are the main questions of the book and of this talk. First, how did life start on Earth? How did life begin here on Earth? And second, are we alone in the Milky Way, first of all, and perhaps even in the universe as a whole? These are the two main questions we try to answer in this book, and I will try to answer in some way at least in this talk. Now, oddly enough, you may know that for hundreds of years, humans thought that they know the answers to these questions. For example, how did life start? Some deity created it. This is from Michelangelo's painting, of course. And that's how life started. What about the Milky Way? The ancient Greeks also had mythology about that. The Milky Way, they say, it was formed by Hera, the goddess, spilling milk because she didn't want to feed the baby Heracles. Now, of course, today we think of these things a bit differently. And I will start with life on Earth. Here is Earth, which is very beautiful, and therefore we should, not do anything to harm it. And then moving from Earth in terms of the search for life, I will move through the solar system. Our solar system has 4 terrestrial planets, which are rocky planets like Earth. There is Mercury, Venus, Earth, and Mars. Mercury is way too hot to ever have had anything. I will talk briefly about Venus and Mars, and like I said, I will definitely spend some time on Earth. Then we have the gas giants, Jupiter, Saturn, Uranus, and Neptune. They are gas giants, so they are really not rocky planets, and we don't think there can be life on them. But they also have many moons. Jupiter has 101 known moons. Saturn has now 285 known moons. Even Uranus has 28 moons and Neptune 16 moons. I will say a little bit about the possibility of life on some of those moons. Now, when we talk about life, we don't try to define life because we did not find that to be particularly useful in understanding how life started. But life is characterized by 4 processes that have somehow to seamlessly combine. And they are metabolism, which means that a living cell is capable of taking materials, energy from the surrounding and use those in order to do what it needs to do. There is genetics, which means there is an information system that is responsible both for processes and also for passing information from one generation to the next. There is compartmentalization, which means all life as we know it is made of cells. There are cells of life, and when we say trying to generate life in his lab, I mean really trying to make a living cell. And finally, there is catalysis, which means there are some agents that speed up and help chemical processes happening. And we need for all of that to somehow happen together. Now, for many years, and I really mean many years, many decades, there was a serious problem that was regarded as perhaps being insurmountable. And that is that when you look at modern life today, you find that it is extremely self-referential or recursive. What I mean by that is that, for example, to do life, is made of those information system, DNA, RNA, and then it's made of proteins. And to make proteins, you need DNA because that really gives all the information and all the orders how to do it and so on. But to make DNA, you need all kinds of catalysts, which are themselves enzymes, which are proteins. So to make proteins, you need DNA. To make DNA, you need proteins. So this is a bit like this Escher drawing of one hand drawing the other. And this was seen as a very difficult problem because obviously it creates serious chicken or egg problems. You know, what came first, the chicken or the egg? This problem was eventually solved, excuse me, when two scientists, Thomas Cech and Sidney Altman, discovered that RNA actually can also work as a protein enzyme. This was a momentous discovery. RNA, which is an information molecule, also can work as an enzyme, which is a protein. So what that meant was that RNA could be the chicken and the egg, if you like. And this led to the idea of the RNA world, which means that life on Earth, excuse me, this is early in the morning for me, so I'm a little bit still, my voice is not fully warmed up. It means that life on Earth could have started just with RNA, no DNA, no proteins, just RNA, because RNA could work both as the information and as the protein enzyme. Now, this idea is fantastic because this means that if I want to understand the origin of life on Earth, it is enough perhaps to understand the origin of RNA. If I can find out how RNA started on Earth, then perhaps this is how life could have started. And that means that we have, first of all, to look at what is RNA made of. And RNA is made of a backbone, which is made of phosphates and sugars, and then 4 nucleobases, which for short are called C, G, A, and U, standing for, cytosine and so on. So these are the names of those, and they have all the information. All the information is in those nuclear bases. So the question is then, how do you make these 3 components, phosphates, sugars, and these nuclear bases? Now, it turns out phosphates are not a big problem because on the early Earth, there definitely were phosphates already around. So the question really is how to make the sugars and how to make those nuclear bases. Now, in what follows, I will introduce a little bit of biochemistry. Some of you may be a bit rusty on your biochemistry, so I don't expect you to look at all the precise chemical reactions. I will just try to give you what are the basic principles that are at work there. Just as an amusing aside, it turns out that the initial molecules that we think started life are molecules that today are considered either very powerful poisons like cyanide or formaldehyde, or have a very bad smell like hydrogen sulfide, which is, what gives rotten eggs their smell. So life somehow started with that. Why with these? I'll tell you why. Because the nuclear bases, they have in them the combination of carbon and nitrogen, and these molecules, the cyanide and so on, has already carbon and nitrogen in it, so this is what helps it do its thing. So we need this cyanide, this CN combination, carbon, nitrogen. And the way we think that happened on Earth was that there was hydrogen cyanide in the air, and that rained onto the surface. Then in the surface, all kinds of metals came from within the Earth. In particular, in this case, we're talking about iron. And that formed ferrocyanide, which is something that is like a salt that is combining iron with the CN from the hydrogen cyanide. And that salt has the good property that it actually comes out of the solution of water that was on the surface of the earth and makes these layers of salt. It can make these layers of salt at bottoms of lakes and so on. Now, of course, later we had to still free this CN from its ferrocyanide, from the iron. And to do that, you need heat. And that's the reason why we think that early life probably started in volcanically active areas where you could have, it's hot there and there are lava flows that when they flow over, the lava flows over the surface, it can actually release the CN from its ferrocyanide. Now, here is one thing where I don't need you to look precisely at what is written here, but I want to give you the principle, and that is the following. I told you that RNA is made of a backbone that has sugars and phosphates, and then there is this nucleobase. Now, one temptation may be, okay, so maybe the way it formed on the early Earth is that the sugar, ribose, combined with the nucleobase, and then later phosphate was added to that. Well, researchers tried to do that, and it doesn't work. They couldn't make the sugar and the nucleobase combine chemically and do what was needed. Instead, what they found was that you can form some intermediate molecules that are called 2AO. 2AO stands for 2-aminohexazole, and RAO in particular, which is ribosaminoxazoline. And those then intermediates, they can then give you what you need. So instead of taking two building blocks, putting them together, you instead form some intermediate, which then gives you what you need. So that is this idea. And RAO, it turns out, has this additional advantage that it crystallizes. So if you had this water and in it were all these chemical reactions happening, RAO could crystallize, and these crystals could get out of the solution and again accumulate in layers, and then those layers could be further activated. Now, this is slightly more complicated, but again, I will give you simply the idea. So you have this crystalline RAO, which is a good step, I said, because it's a good intermediate. And then you can add to it something like it's what is marked here as HCCN, which is cyanoacetylene, doesn't matter what it is. And it creates a molecule that looks a little bit like what you need, but it's the wrong type of, it has the wrong shape. It's a little bit more like a mirror image of what you need. And the fact that it's a mirror image doesn't help you. So how do you get out of this? People tried for years to try to convert this molecule into the one that you actually need. Eventually, what they discovered is that if you add hydrogen, sulfuric hydrogen to this, it actually does something interesting. The sulfur replaces the oxygen there. Now, this sounds like a bad idea because not only you still have the wrong geometry, namely the mirror image, but in fact, you instead of having oxygen there, you have sulfur. But then it turned out that if you irradiate these molecules with ultraviolet radiation, which is marked here by the H at the bottom, then it flips the molecule to the correct configuration, and then it turns out it's really not difficult to replace back the sulfur with the oxygen. So just notice here that what was needed was the sulfur and the UV radiation. This is why this entire cycle is called the cyanosulfidic photoredox chemistry, because it uses the cyanide, the sulfur, and then the ultraviolet radiation. Let me give you a partial bottom line. I told you that there are 4 nucleobases, 4 nucleotides from which RNA is made, C, U, G, and A. Out of those, researchers now found ways how 2 of those, C and U, can be formed precisely from the conditions that we think existed on the early Earth. So 2 out of the 4 nucleobases could have formed on the early Earth with the conditions existing. You may ask, okay, what about the other 2? Well, people are working on that intensively. They have still not managed, but there doesn't appear to be a showstopper in all of that, and they hope that they will find a way how to make the other 2 nucleobases that form RNA. Next, they found something else. The proteins that are in life are made out of 20 building blocks that are called amino acids. There are 20 amino acids that form all the proteins that form life. The same precise chemistry that makes C and U was found to also make 12 out of the 20 amino acids, which means we are more than halfway there. The same initial conditions on the Earth that we think existed on the early Earth, we know how they could form 2 out of the nucleobases, 12 out of the 20 amino acids that form proteins. This still leaves one thing, and that is, in order to have a cell, you also need to have a membrane that surrounds the cell. Now, why do you need a membrane at all? Why do we need to have cells? Why could life not have started without having these closed cells? Well, there are 2 main reasons. One is the cell allowed all the components to stay where they need to be instead of just floating away and, dissolving somewhere and so on. That's one thing. But the second thing is even more important. It was needed to have Darwinian evolution, I mean at the molecular level, not to species. What does that mean? Darwinian evolution means that you continuously improve things, and those that are best fitted, they are the ones that survive. Now, if you don't have cells, suppose that you have, an RNA that now works better, a little bit better as an enzyme, as a protein enzyme. Well, if you don't have a cell, then these molecules get diffused where you are, and you cannot really use them to get the best benefits from that. If you have it all in a compartment, then these things can feed themselves and you get better. So you need to form these membrane walls that form the cells. Now, the membrane walls, when you look at today's cells, they are made of some fatty things, called lipids, and they are quite complicated. So the original one was probably a much simpler type of wall. It turns out, however, that even making this wall, while relatively easy, the simplest walls that you can make are such that they don't hold things for very long. Very quickly, things can pass through them. And that means that if you allow everything to pass in and out, then you lose this business of doing the Darwinian revolution. So evolution, sorry, not revolution, evolution. So you need somehow for these walls they do need to be able to transport things, because this is what cells do. They transport, things are not needed out and things that they are needed in and so on, but they need to have some time to work on those. And it turns out that raindrops, which really means in the lab distilled water, actually can help with that because they manage to enhance the resistance of the walls of these lipid walls to transport things, at least to hold it there for a while, enough for this Darwinian evolution to work. So I now give you the real bottom line of this whole thing. What we found is that from the conditions on the early Earth, RNA, well, at the moment, 2 out of the 4 nucleobases, but also the sugars, proteins, 12 out of the 20 amino acids, and the lipid precursors, they all can be formed from the same chemistry that we know existed on the early Earth. So we are really more than halfway there, and there is no showstopper as far as we can tell. Some of you may have heard about the famous experiment by Miller-Urey decades ago, where what they did was they put in a glass tube. Here is actually their actual experiment. They put some gases that they thought represented the early Earth atmosphere, and they passed some electric sparks through it, trying to mimic lightning. And they found that they generated lots of amino acids or amino acid precursors and so on. And this was being regarded as if this means that starting life on Earth was very easy. While it is true that the Miller-Urey experiment acted as an inspiration for many research in the origin of life, we know today that the result that they obtained was actually not helpful. First of all, I mean, they guessed wrong about the atmosphere, the composition of the atmosphere of the early Earth, which we now know much better. But second, what is really needed is very high concentrations of a few key molecules rather than thousands of molecules that most of which are really not helping at all. So this is the results of the Miller-Urey really did not show that life was very easy. They did not show that at all. The same, by the way, is true. A couple of years ago, this asteroid was found, asteroid Bennu, and they found in it lots of sort of amino acids and things, and was saying, there were newspaper articles saying, aha, great, this means that you could start life and so on. No, you couldn't. You don't need thousands of small quantities of amino acids or any other life molecules. You need very high concentrations of a few key ones. When did life on Earth start? There is strong evidence that life started in these things called stromatolites, which show this layered of sort of kind of bacteria, and it started about 3.5 billion years ago. Every few years, there is a suggestion that maybe somebody found life much earlier than that. Usually, but not, it doesn't mean that it will always be like this. It is found later that those was not really life, but some other things. I just remind you that the Earth is about 4.6 billion years old. We see the first evidence of life about 3.5 billion years ago. Where did life start on Earth? Again, many accounts in still many books, even, and certainly newspaper articles would try to convince you that life started at hydrothermal vents deep under the ocean. I will say that we argue that that is not possible, in fact, and there are many reasons for that. It is true that near these hydrothermal vents today, there are lots of life forms, but that doesn't mean that life started there. And why do we think that it didn't start there? First of all, there is no plausible path that has been demonstrated for molecules of life to form there. Second, I told you many times now that you need high concentrations. You cannot get that at the bottom of the sea. Everything gets diluted. And also you need this ultraviolet radiation, which there was copious amount of it from the early sun, but not that radiation doesn't reach the bottom of the ocean. So where do we think life started? Actually in smaller ponds and lakes, where you could have a large variety of concentration mechanisms, like wet dry cycles on the sides of this pond, freeze thaw, which also concentrates things, evaporation, which also concentrates things, crystallization, as I pointed out about RAO, and of course they have access to the UV radiation. In particular, alkaline carbonate lakes or crater lakes, we think are best for this. This is where we think things probably started. This finishes what I wanted to say about life on Earth, and I will now move to searches for life in other places. So one place where we looked a lot and are still looking is Mars, our nearest planet. Mars, we once thought that when I was a child, people even thought that there is a whole civilization there. We now know that it just looks like a dry desert, and it hardly has any atmosphere at all. It just has a whiff of carbon dioxide, and that's it. But there is no water on the surface today, but we know that there was water on the surface of Mars about 4 billion years ago. We see lots of evidence for that. Here is just one of them where water was flowing on the surface of Mars. So it is very possible that life started on Mars some 4 billion years ago, but then later it didn't further evolve because Mars is a smaller planet. It lost its heat, it lost its atmosphere, and so on. So life couldn't evolve. We know that there is still water underneath the surface, some 6 to 10 miles deep, from this InSight lander that basically measures seismic activity, and we found that there is liquid water a few miles down. So, at one point we will look for that. Some of you may remember that there were 2 Viking landers that landed on Mars early on. And there were even experiments that were interesting that they scooped some ground from the surface of Mars, combined it with some nutrient, and they appeared to show some metabolism. But then searches for any organics in that Earth material, Mars material, did not find any signs of that. So today, I would say most researchers think that the Viking experiments did not discover life on Mars. There were big stories. I mean, they made it even into a White House declaration about this meteorite, ALH 84001. This meteorite was thrown from the surface of Mars by the heat of some asteroid or something on the surface of Mars. It moved through space. So it was hit off the surface some 4 billion years ago or something, and then moved through space. And eventually, after moving through space, it landed up in Antarctica. And it was found that it had some structures that were at first interpreted as if these were signs of life. Later, it was found that pure chemical abiotic, namely non-biotic processes could actually form those structures. So again, we don't think now that showed any signs of life, that meteorite. There is this rock which shows some signs of organic. The Perseverance rover, which took here its own selfie, is there in that region, and it took some samples, and if those are brought to Earth eventually, we will have to look, we will be able to look at them more carefully and find out what's going on with that. I will tell you that my personal opinion is that if we don't find any signs eventually of early life on Mars, not life today, life that existed 4 billion years ago, I think that would be actually surprising because, Mars and Earth form from roughly the same region of the disk that surrounded the early sun. So it is very likely that life might have started on Mars, even if it hasn't evolved. Okay, Venus. Venus, for many years, we thought that there cannot be any life on Venus because Venus is very hot. In fact, it's so hot that on its surface, lead would melt. But in the past 4 years or so, there were suggestions that in the upper atmosphere of Venus, they found the presence of this molecule called phosphine and also ammonia. Now, phosphine on Earth is created by life processes. So if true, this can be interesting. Although, there are processes other than life that also can form phosphine. Now, the good news here is that there are a few missions planned to go to Venus, and actually even probes to go through Venus's atmosphere, and they will tell us more about, first of all, whether the detection is real, and are there any processes that could form some form, of course, of primitive life in the atmosphere of Venus. I already mentioned Jupiter itself, which is a gaseous planet. Here, look how its atmosphere looks from up close. Cannot support life, but it has moons, many moons that perhaps can. Europa is one of them. We have strong evidence that Europa, well, on its surface, it has a very thick layer of ice, miles deep layer of ice, but underneath that ice, there is a big ocean, actually, of liquid water underneath the surface. Now, I already told you that we don't think life started in liquid oceans, but liquid oceans can support life, maintain life once started. So, for example, if 4 billion years ago a rock was knocked off the surface of Mars with some life forms in it, and that actually flew to Europa, it's possible that life was sustained there. So this is why it is important to look. And the Europa Clipper, which was launched, is supposed to arrive to the Jupiter system around 2030, and it will continue to explore Europa and a few other moons. Saturn, also like Jupiter, is a gaseous planet, so it doesn't have life on its own, but it has a few moons that are very interesting. One is Enceladus. Enceladus not only has a large ocean underneath its thick layer of ice, but we have seen plumes coming out of Enceladus, which means that there are cracks in that ice. And that is very helpful because it means that we may not have to dig through that ice, but rather it is enough that a spacecraft flies through the plumes, as has already at some level happened, and determine very accurately their composition and see if there are any organics there. And it appears that there are some things there, organics. Again, this is not where life we think started, but where maybe it can be maintained. Titan is another moon of Saturn, and it is a very exciting, intriguing moon because in addition to having a liquid water ocean underneath its icy surface, on its surface, it actually has lakes, but lakes not of water, but of liquid methane. And that allows, in principle, for the possibility of even two types of life forms. One, life as we know it in the water underneath, and one for life as we don't know it in the liquid methane on the surface. However, I wouldn't hold my breath for life in this liquid methane because the temperature is extraordinarily low, and it is virtually impossible to have any interesting chemistry in that. But it is still exciting, and there was once a plan by NASA to land something like a boat on one of these lakes. That particular plan is no longer in effect, but one day we may study those lakes. I now move on to outside the solar system in our galaxy, and we know that there is lots of star formation. Here is just one image of by the James Webb Space Telescope, how new stars are being born in clouds of gas and dust. This is the famous Eagle Nebula, again, clouds of gas and dust, inside which this is how new stars are formed. This is the same Eagle Nebula, only seen by the James Webb Space Telescope, and because it looks in infrared, actually much of the dust becomes transparent, and so you can see through some of these columns of gas and dust. We have known for quite a while from Hubble observations that many young stars have around them these disks of dust and gas, which are precisely the same things from which our own solar system formed, namely the planets formed from these dusty disks around young stars. With the James Webb Space Telescope, we find also, we see early stages in planet formation, and that is all very good. Now, here is the fantastic progress that has been made. Until 1992, we didn't know of a single planet outside the solar system, not one. In 92, we discovered some planets, but they were around pulsars. Pulsars are these very, very dense objects, and we don't think that that formed in supernova explosions, and we don't think that there could be life on those planets. But in 95, we discovered the first planet around a sun-like star, and since then, we've discovered more than 6,100 extrasolar planets revolving around stars other than the sun. And, if you take that and do the statistics for the whole galaxy, then there are, in our own galaxy, there can be, hundreds of millions and maybe a billion planets that are a bit like Earth. I mean, not all like Earth, but planets that revolve around stars that are not too different from the sun, again, up to maybe a billion. And this allows us to do very interesting things. In particular, the following thing, what is called transit spectroscopy, which means, if you have a star and you have a planet revolving around it, then sometimes our line of sight is such that the planet exactly goes in front of the star from our point of view. When that happens, the light from the star passes through the atmosphere of the planet on its way to us, and then we can do spectroscopy of that and determine the composition of the atmosphere of that planet. And if we do that with enough accuracy, which we are getting there with the James Webb Space Telescope, and especially with the next generation of such telescopes, then we can actually determine whether there are biosignatures, meaning molecules that indicate the potential presence of life there. And that is what we're doing. In particular, there is a TRAPPIST-1 system, which has 7 planets, a bit like Earth, also a few of them in what we call the habitable zone, which means the distance from the star that allows for liquid water to be on the surface, which we think is something required for life. And in particular, one of those, TRAPPIST-1e, may have an atmosphere with nitrogen and methane. We say now no carbon dioxide. This is just an artist's impression. So we're starting to get there. There's been another exoplanet that has made some noise in the media, K2-18b, which showed dimethyl sulfide, which again on Earth is created by life processes, although that's not the only way to create that. So we don't know yet whether this is a sign. I'll just mention in passing that some of you may have heard about the Drake equation, which tried to give the probability of having a civilization somewhere in the Milky Way. The astronomical factor in these equations, probability factors, we now know from astronomy, but all the remaining factors that have to do with whether life develops or not and so on are really unknown. So this equation does nothing more than just exemplify our ignorance. Now, of course, there are many galaxies. So if you look at the universe, there are lots of galaxies. This is the James Webb Deep Field. The estimate now is that in our observable universe, there can be about 2 trillion galaxies. So you have to ask yourself, okay, so people tell me, oh, so 2 trillion galaxies, and each one of them has maybe 100 billion or maybe even a trillion, maybe 100 million or maybe even a billion of planets. So of course there must be life somewhere. No, unfortunately, not of course. And why do I say that? Because at the moment, we actually don't have a clue of what is the probability for life to emerge, even if all the conditions are there, because we only have one example of life so far, and that is the Earth. So since we don't know that, if we have 10 to the 20 planets like Earth and so on, how do we know that the probability of life emerging is not smaller than 10 to the minus 20? So we cannot actually answer that. Dyson spheres are the ideas that if you have an intelligent civilization, it may build structures to collect the energy from its central star. We have not seen yet signs to that. What would a distant civilization look like? Well, they cannot hide the fact that they have to have waste heat, which would be observed in mid-infrared. WISE Observatory looked at 100,000 galaxies, found 5 that have strange mid-infrared emission. This is something that I could talk on for a long time, but I wouldn't. And that is that maybe biological evolution is just a very brief phase in this, because sooner or later we are being replaced by machines. And, we have started to see something along this direction with AI. So it is possible that, okay, maybe not in 5 years, maybe not in 10 years, maybe not even in 100 years, but can you actually tell that in 1,000,000 years, which is nothing compared to evolution, Darwinian evolution, that in 1,000,000 years, the dominant species will not be a machine? If that is the case, then the way we are looking now may actually be inappropriate. And so the bottom line is, At the moment, I actually cannot answer the question whether life is an inevitable outcome or a freak accident that happened on Earth. There are two things that I want to finish with. One is very important. You see, you may get depressed from the fact that, okay, there may be 1 billion Earth-like places in the Milky Way, and there are maybe 2 trillion galaxies. So our physical existence has become, over the years, more and more insignificant. However, here is the thing. You see, all the elements in our bodies were actually forged at the centers of stars. In the Big Bang, there was only hydrogen and helium and trace amounts of other things. All the other things, carbon, oxygen, iron, and so on, were formed in stars. And then eventually there were either supernova explosions or a planetary nebulae, slower ejection of outer layers, and from that planets formed and eventually life formed. In other words, not only are we in the universe is inside us. So we have an intimate connection to the universe. And in that sense, we are, not only that, everything I described was discovered by us. By us, I mean humans, yes? So in that sense, we are very central to our universe, because the universe, we found the universe expanding just in the rate that our knowledge has expanded. So in that sense, we are central. And I will finish with this. Philosopher Immanuel Kant wrote once, 2 things awe me most: the starry sky above me and the moral law within me. If I change that phrase to more modern terms, I would say that there are 3 origins that we're trying to explain. One is the origin of the universe, the other is the origin of life, and the other origin of consciousness. Now, we have made lots of progress in understanding the origin of the universe. We know that the universe started from a hot, dense state, which we call the Big Bang. I showed in this talk that we have made a lot of progress in understanding the origin of life. We're not yet there. I mean, there are many questions remaining, but we've made lots of progress. We've made somewhat less progress in understanding the origin of consciousness, even though there is progress there as well. There are now, at least 4 leading theories of how consciousness happens. We still don't know whether consciousness is an emergent property, which means that in any complex enough system, eventually consciousness appears, or not. And this makes a big difference. But people are starting to test these kinds of ideas as well. So I will finish here and remind you that this is based on this book, Is Earth Exceptional? The Quest for Cosmic Life. And I will take questions. Thank you.
Thank you, Professor, for your brilliant and informative and inspiring lecture. I would like to express my sincere gratitude for you for sharing such profound insights, which made us really think broader. So I think this has left us many interesting questions as well related to habitable planets and occurrence of life itself. Let us take a few such questions now. Before taking the questions, let me remind again, the process for asking the question is scanning the QR code that is shown on your screen, and by using the Google Form link that is shared over chat. So please do ask your questions. Yes, first question, please. It is by Om from VNIT Nagpur.
Excuse me, just a second. Should I escape from my presentation to see the question?
Yes, sir. Actually, we have already stopped your presentation. You need to open the window of Zoom on your system.
So where do the questions appear?
On the Zoom window on your system.
On the Zoom window. In the chat? Is it in the chat?
No, not chat. On the screen itself.
Zoom application.
I'm not sure where.
Just like you were sharing the screen, it is also shared as screen here.
Well, I was simply seeing the. I was simply seeing my thing. Oh, okay. Now I see it. Yeah. Okay.
Okay. Okay. Thank you. Thank you for confirmation.
Oh,
So this question is from Om. Okay. It seems you have shared your screen again.
yes, I know.
Okay, stop sharing.
Okay.
We have
Yeah.
stopped sharing and shared our screen. I hope it is visible to you.
Yeah, I see now the question. Yes.
Thank you. Thank you, sir. So this question is from Om from VNIT Nagpur, India. So he's asking, why do Earth, Mars, and closer to Sun have less number of moons, while Jupiter, Saturn, and Uranus have large number of moons? Is there any reason for this?
Yes, there are reasons. I mean, typically, first of all, the number of moons also scales somewhat with the size of the planet, because if you had more material in that area, you could form the planet and you could form its moons. Earth is, 1,000 times smaller than Jupiter, so there was much less material when it formed. The moon that we have was actually formed by the fact that a Mars-sized object collided with Earth and tore a piece of it, and that's what formed our moon. Otherwise, we would not even have had a moon.
Thank you, sir. Thank you for letting us know that. Can we have next question, please? This is from Professor Tejinder Singh. He is from Tata Institute of Fundamental Research, India. His question is, what physical principle favors formation of RNA molecule or just having separate components, sugar, phosphate, and bases? Is it because the molecule has negative binding energy? Also, what physical principle causes a cell to divide as DNA to replicate? Thank you.
Yeah, so, I cannot answer this, with lots of knowledge. I mean, the thing is that life did not have in principle to start with RNA. In fact, lab experiments show that there are other molecules that could have acted perhaps even better than RNA. However, it turns out that when they try to do those molecules in the lab, at least, then RNA seems to win in the sense that it is both replicating faster and more resistant to being destroyed. And this is what appears to be make RNA win in these types of situation. So there isn't one fundamental physical principle. It's a series of, if you like, filters that somehow at the end favor RNA over different types of structures.
Thank you, sir. Thank you. Can we have next question on screen, please? It is from Pradeep Kumar from Kendriya Vidyalaya, Sangathan, India. With due respect and sincere thanks for your valuable insights, I humbly wish to ask, based on the theoretical frameworks you discussed, to what extent has modern science been able to successfully replicate the transition from prebiotic chemistry to self-sustaining biological life?
So only partially. The answer is only partially. As I said, for the moment, we can do 2 out of the 4 nucleobases, 12 out of the 20 amino acids, and some very, very simple lipids. This still leaves a lot of work to be done, but it does appear to show that it is possible, but it may be very rare, and indeed, in most cases, it may not succeed, and we may be one of those rare cases where the process succeeded. So I cannot say that we have proved, almost like in a mathematical sense, that life started from abiotic chemistry. But all I can say is that we showed that there are pathways that perhaps life could have gone in that. Even if we succeed when I say we, I personally don't work in the lab with that. I'm a theoretical astrophysicist, but Jack Szostak and his colleagues, if they succeed in making at the end, a living cell in the lab, it doesn't necessarily mean that life on Earth started exactly like that. It just shows that that is a plausible path. So, to speak in mathematical terms, it is like an existence theorem. It doesn't prove that this is how things actually worked.
Thank you, sir. Thank you. I hope it has helped us a bit. This is a question from Kumar Ravi from Swami Vivekananda University, Barkpur, West Bengal, India. So in the context of the origin of life, we often think of a transition from inorganic chemistry to organic molecules arising, perhaps accidentally, through natural process. The Miller-Urey experiment is a classical example demonstrating this step. Could you highlight other key experiments in roughly chronological order that have significantly shaped our current understanding of how life may have originated? Also, are these developments discussed in detail in your book?
Yes. So, look, I would say that, in my opinion, two of the most productive researchers who have made a big difference um, in um, in this origin of life experiments are Sutherland in the UK and Szostak, my co-author, in the US. But of course, there have been many others, and I pointed out the really monumental discovery of Czech and Altman, that led to and Leslie Orgel also, who led to the idea of the RNA world, which is crucial in our current understanding. And yes, all of these things are described in our book.
Thank you, sir. Thank you. I hope this helped him, and maybe he will go through the book as well. Can we have one more question with your permission?
Sure.
Yeah. Last question for current talk. It is again from Dr. Bharat Pandey, Government PG College, Raniket, India. He's asking, sir, I want to ask if phosphine and ammonia are detected in Venus's atmosphere, how can we distinguish whether they come from unknown chemical process or possible microbial life?
So you're right. I mean, so we have to make sure that they have really been detected. This would be because there have been some questions about the detection itself. But like I said, there are 3 missions planned for the atmosphere of Venus. So we will know that part. Then we will have to see whether there are any other chemical compounds or things that can show that this is part of some sort of a life process, or just the fact that it was formed via non-biological processes. So really, I think we're in a very good situation in the sense that there are these missions planned. So unlike in cases of extrasolar planets where they are very hard to really research, in this case, we will have a whole series of experiments that will clarify the situation about Venus. To be honest, I'm not holding my breath about life on Venus, but it is very interesting nonetheless.
Thank you, sir. Thank you. Thank you very much for this wonderful question and answer session. We still have many more questions from the audience, but due to limited time and schedule followed, we are limiting ourselves here. With your permission, we would like to conclude here.
Sure. Thank you very much.
Thank you. Thank you very much, sir. On behalf of Bhaktivedanta Institute and all the audience, I would like to once again express our sincere gratitude to you for sharing your wonderful insights and profound knowledge on interesting and intriguing topic is Earth exceptional. So we hope all the audience have gained some insights about inhabitable planets and existence of life itself, occurrence of life itself. So with this, thank you, sir. Thank you once again. And we hope to see you again in our future events.
My pleasure. Bye-bye.
Thank you, sir. Moving on, our final speaker for today is Professor Tejinder Pal Singh. He is a visiting professor of IUCAA and formerly with TIFR Mumbai. He will be speaking on this interesting topic, quantum theory, gravity, and the cosmos. So once again, a gentle reminder to all the audience. So in order to ask the questions during the session or after the session, please do scan the QR code, take a screenshot of this QR code and keep it with you. Or a Google form link will be shared over chat so that you can use it for asking the question. Without any further delay, let me take the privilege of introducing today's final speaker, Professor Singh. Tejinder Pal Singh is a distinguished theoretical physicist, formerly with the Tata Institute of Fundamental Research, renowned for his work on quantum foundations, gravity, and cosmology. He earned his PhD from TIFR in 1989 and subsequently held postdoctoral and visiting positions, including at the Inter-University Center for Astronomy and Astrophysics. For a career spanning more than 3 decades, he progressed through various academic roles at TIFR, contributing significantly to research and mentoring in high-energy physics and quantum theory. His research focuses on developing deeper connections between quantum mechanics and gravity, with notable works on spontaneous wave function collapse models, quantum to classical transitions, quantum interference in time, and generalized theories of gravity. Professor Singh has also contributed to studies of cosmological constant problems, dark energy, gravitational collapse, and torsion-based gravity theories. Widely respected for his conceptual clarity and theoretical insight, he continues to be active in advancing foundational questions in modern physics. And now, without further delay, it is my great pleasure to invite Professor Singh to deliver his lecture. Sir, please.
Thank you for your very, very kind introduction. Can you hear me?
Yes, sir. We
Yeah.
are able to
Yeah.
hear you and see you.
Yeah, I would also like to thank Bhaktivedanta Institute for giving me the opportunity to present these ideas here. It is my second interaction with the Institute. I was there physically in person last year in Kolkata for the quantum mechanics, foundations of quantum mechanics meeting. It was a pleasure. It's a pleasure to be back. I also want to thank our previous speaker, Professor Livio, for giving such a beautiful lecture and setting a very nice flavor with his excellent and enjoyable presentation. So I have to try to meet those high standards. And also there is now a change of flavor, yeah. we are going from understanding life in the universe to the more physics questions. So, my point in this talk is that if we want to understand how the universe began and how it will end, we must first have in hand those laws of physics which are necessary for that work. So, right. So, what is the connection between cosmology and physics? Our understanding of the universe is limited by our understanding of the laws of physics. In particular, the laws of quantum theory, of gravitation, and of particle physics, basically all of fundamental physics. If we don't understand those laws well enough, we cannot successfully and reliably understand the beginning of the universe. And there is currently a limitation to our theoretical understanding. Like we don't have a theory of quantum gravity. It's not that, it doesn't mean we will never have, but right now we don't have. So the highest energy scale that we can understand theoretically today is about TeV, it's about, which is around 1000 GeV, 10 to the 12 electron volts. In the early universe, this is the electroweak symmetry breaking scale. We don't know how the universe began. If it began with the Big Bang, then the highest energy scale, assuming that it is finite, would be the Planck energy scale, which is 10 to the 19 GeV. And what we have understood so far is a much lower energy scale, about 1000 GeV. So we understand physical laws up to about 1000 GeV, and we have to go all the way up to 10 to the 19 GeV. So at this energy scale, at the TeV energy scale, the universe was about 10 to the power minus 12 seconds old. So assuming it began with the Big Bang, and we know it is 13.8 billion years old today in the standard cosmological model, we understand physics all the way back to 10 to the minus 12 seconds, which is very impressive. But we need to understand these before 10 to the minus 12 seconds also, because Planck time, the smallest fundamental unit of time, Planck time, is 10 to the minus 43 seconds. So although 10 to the minus 12 is small, 10 to the minus 43 is much, much smaller. It is about 31 orders of magnitude less. So that whole 31 orders of magnitude, we don't know what happened there. We can only make ideas. So what was the universe like before 10 to the minus 12 second? We do not know. So what is holding us back? Various reasons. Why don't we know before this time? Well, particle accelerators like the LHC, the Large Hadron Collider, have not yet crossed the TeV scale. People want to make accelerators with, it can probe higher energies, but it is extremely expensive. But it is not just experiment. Theory also is lagging behind. In fact, theory is lagging behind experiment. Why do I say that? Experiment has given us a lot of data. The standard model of particle physics, strong force, weak force, electromagnetism, all have been discovered. Why are there these three forces? Why do they have these particular symmetry groups, SU3, SU2, U1? And most importantly, the experiments and the accelerators have given us dimensionless coupling constants, like the fine structure constant or the ratios of masses of elementary particles. We need to explain why these dimensionless constants take these particular values. We cannot say that, oh, we don't know the answer because we don't have an accelerator beyond TeV. Is that the real reason? We don't know. Maybe theory is lagging behind. We do not have a theory of unification of all forces. We do not have a theory of quantum gravity. So to understand the beginning of the universe, we must first develop quantum gravity and unification And my thesis is that the reason we are stuck is because there are foundational problems of quantum theory which need to be first solved to make progress towards quantum gravity and unification. So my work over the last couple of decades has been in this direction to address specific questions in quantum theory. And in the process of solving those questions, I found that we are inevitably led to a theory of quantum gravity and a theory of unification. And that is the story I want to tell you today in brief, and how what that is then telling us about cosmology, or about the universe at large. Right. So there is one particular foundational problem of quantum theory which is central to this whole development. I call that the problem of time in quantum theory. So what is the problem? In quantum theory, evolution is described using a time parameter which is classical. What does this mean? So when you write the Schrodinger equation, IH bar del psi by del t equals h psi, that t that is appeared, that time parameter is not quantum in nature. It is part of a classical space-time. You could say that time is not an operator. Position of a particle is made into an operator, but time is not made into an operator. Time is classical. It's a real number. And that is a problem in the following sense. Why? So time is part of a classical space-time. Classical space-time is produced by classical macroscopic bodies such as stars and galaxies. So according to Einstein's theory of general relativity, space-time has curvature, and the curvature of space-time is the same thing as gravitation, and this is produced by macroscopic large bodies, stars, galaxies, clusters of galaxies. But it is not just the gravitational field, it's not just the curvature, it is space-time itself, what we call the space-time manifold. X, Y, Z, T are the coordinates of space-time. That is a fabric, that is the underlying arena in which bodies live. I am saying, okay, I will not go into the details today, that if you want to meaningfully talk of the space-time manifold itself, the fabric of space-time, the points of space-time, then the universe must be dominated by classical macroscopic bodies. This can be made a formal argument. I will not go into it right now. So what am I saying? Classical space-time and classical macroscopic bodies cannot exist without each other. If the universe is dominated by classical objects, the space-time manifold will be point-like. If the space-time manifold is point-like and if it can be defined as a fabric, it means material bodies must exist. In other words, in my way of looking at it, there is no meaning to an empty space-time. If you think that universe is everywhere flat and there are no bodies in it, I say that that is unphysical. We don't observe such a universe. The only universe we observe has matter and radiation, and it has space-time. I'm saying in order to talk of space-time, you need the universe to be dominated by classical bodies. However, classical macroscopic bodies are a limiting case of quantum systems. So what is going on? Quantum theory needs the external classical time. That classical time is possible to be produced only if the universe is dominated by macroscopic bodies. However, but these classical bodies are a limiting case of quantum systems. You put a lot of atoms together, that is how you get a planet or a star. So you see with this logic that quantum theory depends on its own limit. How? Because quantum theory needs classical time. Classical time is possible only if there are macroscopic bodies in the universe. But macroscopic bodies are a limiting case of quantum theory. So quantum theory depends on its own limit in a circular way. By depending on classical time, quantum theory depends on its own limit. Which means that The description of quantum theory that we have today can only be approximate. It is not exact. It is extremely successful. It is matching the experimental data extremely well. There is no experiment which contradicts quantum mechanics or disagrees with it. But that does not imply that the current formulation of quantum mechanics is exact. An exact formulation of quantum theory will not depend on classical time, right? Because suppose there are no macroscopic bodies in the universe, then there is no classical time. Yes, still I should be able to talk of quantum mechanics. Imagine that everything in the universe today is quantum, is in the form of electrons and atoms, and there are no planets and heavenly bodies, no stars. In principle, such a universe can be imagined even at today's low energy scales. So everything is quantum, so I should be able to have a formulation of quantum theory without having to use classical time. And such a formulation must exist at all energy scales, not just near the Big Bang. Today's universe is dominantly classical, but in principle it need not be so. And although it is said that quantum mechanics does not disagree with any experiment, I would say that that is only half the story. Quantum mechanics is not able to explain why fundamental constants take those values which they do. And my thesis is that that limitation is because we are working with the approximate quantum mechanics even at low energies. When we had this exact formulation of quantum theory, we will understand why fundamental constants take the values that they do. So that is the hypothesis. And so my goal is to build such a formulation of quantum theory in which classical spacetime does not occur at all. And let us start to go towards that goal. Right. So I'll help you visualize where the exact formulation of quantum mechanics stands compared to the quantum mechanics that we have today. So I made this cartoon in which there are three layers: clouds, rain, and terrain, that is ground, what is called terra firma, earth with all its forests, trees, mountains, snow, us. So this is the terrain. So I'm using this analogy that there is a terrain, there is a in between, there is rain, and there is a cloud. And this picture of these three parts of the picture are of interest at all energy scales, even at low energy scales, at high energy scale. The cloud is an analog for the exact formulation of quantum mechanics. So what is happening in the terrain, as the quantum mechanics that we know today, there is a base. Classical matter, the universe dominated by classical bodies, is giving rise to classical space-time. So here you can put also stars and galaxies. This is our classical universe. It gives us classical space-time. In here we also have quantum systems like electrons. So if you want to write down the quantum equation for an electron, you will write the Schrodinger equation for the electron using the time that is coming from this terrain. We are looking for an exact formulation of quantum mechanics in which there is no classical matter. Remember, right? Suppose there is no classical space-time, no classical bodies, everything is quantum. How will I do quantum mechanics? That we call the exact formulation of quantum mechanics. It turns out that over here, there is no distinction between space-time and matter. In a way, easy to understand. Space-time and matter are distinct only when matter is classical. Suppose everything is quantum, like in the cloud. So it's like an electron. The electron is everywhere, and everything is quantum, so everything is everywhere. If everything is everywhere, then there is no space between things. So we think of space as space is that which is between bodies, time is that which is between events. In the cloud, in the exact formulation of quantum mechanics, everything is everywhere all the time. So there is no way to talk of space-time and matter separately. So the distinction between space-time and matter goes away. So I will not talk here of an electron in space-time. We talk of atoms of space-time matter. Okay? So in the exact formulation which is in the cloud, there is no distinction between space-time and matter. We have atoms of space-time matter. Now, when lots of these atoms, so electron also here would be called a particular kind of atom of space-time matter. A quark is another kind of atom of space-time matter. Here, when lots of atoms, such atoms entangle, a quantum to classical transition takes place. A classical universe arises because of spontaneous collapse or entanglement in the cloud. So that I call rain. As an analogy, what is rain? Rain is the process of transition from exact formulation where there is no space-time to a situation where there is classical matter and space-time. Once this transition happens, we have a terrain, and if you have an electron here, you could now describe it using the ordinary Schrodinger equation because you have acquired time. In the terrain, there was no classical time. It turns out that there is a new concept of time. So in the cloud there is no classical time, but it turns out that there is a new notion of time, which I will talk of in a moment. And so you can describe an electron either using the time from the terrain, or you can describe the electron using this exact formulation of quantum mechanics. And this is to be respected at all energy scales. Even in today's low energy universe, it looks like this, but I must still seek a cloud picture which is in the cloud, even at low energies, for reasons that I just described. Okay. So I hope you get some idea of what I am trying to do. Now our goal, mathematical goal, is to construct this exact formulation of quantum mechanics in the cloud. It turns out this is also a theory of quantum gravity. It is also a theory of unification of forces. So that is the significance of addressing quantum foundations. My claim is that we are stuck in theoretical physics, like why does string theory not work? Why does it predict so many different 10 to the power 500 vacua, as we saw in Professor Lidley's talk? It is because it is not addressing foundational questions in quantum theory, like the problem of time. When you address the problem of time, you are actually led to a theory of unification, and I want to, in the next few slides, give you my picture of the mathematics. There will be about 3 slides like this, which are slightly technical, because I want to give you a flavor as to how our group has worked to develop this exact formulation of quantum theory. So there are 5 mathematical ingredients which go into it. I'll give you some idea. The first is number systems known as division algebras. These are number systems in which division is allowed. Like, real number are a division algebra. Complex numbers are also a division algebra. So what is meant, if you have two numbers a and b in a division algebra, if you multiply them and if the answer is 0, then it is natural for us to say that either a is 0 or b is 0, or both are 0. Both cannot be non-zero. If a is like 3 times 4 will not give you 0. If you multiply 3 with something and you get 0, then that something has to be 0. So in a division algebra, if a times b is 0, then at least one of them should be, a and b should be 0. Turns out there are number systems which are not division algebras. Namely, you take a non-zero, b non-zero, you multiply, the answer is 0. One such number system is known as the Sedenions. Sedenions are not a division algebra. Remarkably, there are only 4 types of division algebras: real numbers, complex numbers, this is we know. Then you may have heard of quaternions and octonions. Quaternions and octonions are very important in my work, in this approach. When we want to get rid of space-time, when we want to get rid of classical time, we are going to replace every real number by a octonion. I'll explain what a octonion is. But the fact that in most of physics we have been using real numbers, in classical physics, complex numbers, in quantum mechanics, quaternions are actually basically 4 vectors. We use them in special relativity. We have never until recently used the octonions. They were discovered in around 1850, soon after Hamilton discovered quaternions. A friend of his discovered octonions. But physicists did, until the last 20, 30 years, physicists did not find a use for octonions. But now, in the small community in which we work, called algebraic unification, octonions have become extremely important and interesting. It seems they capture the mystery of particle physics. Why the fundamental constants take those values? It has to do with the octonions. And why the forces, why is there the strong force, weak force, gravity? Everything is related to this 8-dimensional number system. So we'll replace real numbers by octonions. Then we will have a new theory. Again, I'll tell you a few words about it in the next slide. A theory of dynamics called trace dynamics, which was developed by Stephen Adler and collaborators about 30 years ago. It is Newtonian dynamics with matrices. When you do Newtonian mechanics, positions are real numbers. But suppose positions were matrices, but you still write down Newton's laws of mechanics, but with using matrices. That is trace dynamics. We will use something known as non-commutative geometry, which generalizes the Riemannian geometry of general relativity. So what is non-commutative geometry? Is a situation where x times y is not y times x. Points do not commute. See, spacetime is made up of points which are described by real numbers. Those points commute with each other. In a so octonions do not commute with each other. A times b is minus b times a. They don't commute. Quaternions also do not commute. When you have replaced spacetime by entities which are described by such non-commuting numbers, you are in the domain of non-commutative geometry. This generalizes Riemannian geometry of general relativity and something known as the spectral action principle and the use of eigenvalues of the Dirac operator as a description of geometry. Let it pass if this is too technical. The fourth ingredient that goes into the development of this new formulation is something known as Clifford algebras for making spinor states from division algebras for describing elementary particles. Given the octonions, from octonions you can make Clifford algebras. From Clifford algebras you can make spinor states which describe elementary particles. So there is nothing there's nothing free about this process. It's a very rigid structure, so that's why we don't have the kind of, infinitely many vacua that string theory has, because we have started from a foundational principle and work with octonions. Then the octonions dictate everything, there's no freedom left. And the symmetry is described by these so-called 5 exceptional Lie groups, which I'll say a little bit about it, labeled G2, F4, E6, E7, E8, and something known as the exceptional Jordan algebra. I'm sorry this slide is quite technical, but only 1 or 2 more like that, and then we'll talk nice physics. Let us understand this in a simple way. So when we use these ingredients, they help us go from the terrain to the cloud. What do I mean? We know the physics in the terrain. Forget quantum mechanics for a minute. Here everything is done by real numbers. I'm going to go from the terrain to the cloud by replacing real number spacetime by octonions, by replacing position vectors described by real numbers by matrices. So points, real number points become octonions, and real number valued position vectors become matrices. So we jump from here to here in a very nice and intuitive way. Just replace real numbers by octonions, and dynamical variables which are real numbers, replace them by matrices. It's a very intuitive way of doing things. So let me describe that intuitive process in a little more detail. In the terrain, this is physics, college physics. Suppose normally if you have free particles in space-time, it is described by a position vector qi, q0, q1, q2, q3 in special relativity. These are the four components of the position vector q of the particle. So Q in boldface, it is the position vector, four-dimensional. These are its components, and in components you will write it like this. I hat, j hat, k hat are the usual spatial unit vectors, and t hat is a unit vector in the time direction. So given the position vector, you know that we have to write down equations of motion. This will be the equation of motion for a free particle. It is derived from this action. If you are familiar with the action principle, this the half mv square is the Lagrangian, the velocity. Integrate the Lagrangian over time, you get the action. You vary the action, you get equations of motion. Plus, we have a symmetry. If you make Lorentz transformations on this vector q, it will give you another vector, but the equations of motion will not change. So invariance under Lorentz transformation is a symmetry, and mathematically the group that describes Lorentz transformation is this Lorentz group SO13, which generalizes the rotation group SO3. Okay, so this is the terrain, very simple standard Newtonian physics. Now let us go to the cloud. What will I do? Replace each space-time point by an octonion. There are reasons why we do this. It just gives us the unification theory. And you can ask why octonion. So I'd say because it works. Right now I'll leave it at that level. So what is an octonion? It is a complex number. Real number is just A0. Yeah, that's a real number. If you had A0 plus A1, E1, that is a complex number because where E1 square is -1. Normally we write iota. Iota and E1 will be the same thing. If you have A0 plus A1, E1, you have a complex number. If you had four of these, A0 plus A1, E1 plus A2, E2 plus A3, E3, that is a quaternion, where A3, A2, A1, and A0 are real numbers. If you have 8 of these, it turns out, if you want to make a division algebra, you will only have A0, or you have one imaginary direction for complex number, or 3 imaginary directions for a quaternion, or 7 imaginary directions and a real direction for an octonion. So 1, 2, 4, 8. These are the 4 division algebras. What is an octonion? Each of these EI square is -1. So there are 7 imaginary directions in an octonion. It generalizes the complex number which has only one imaginary direction. And multiplication is non-commutative. EI times EJ is minus EJ times EI. So it's anti-commuting. This is a definition. And if you had an octonion, if you had a quaternion, you would have only 3 imaginaries. In octonion, there are 8 imaginaries. So what are we doing physics-wise? So space-time in the terrain, space-time was a collection of points. Each point is to be replaced by an octonion when you go from the terrain to the cloud. Okay. What else? You have to take this position vector, which had 4 real number valued components like here, replace the position vector by a matrix vector. What does that mean? So instead of bold Q, I have written capital Q mu nu. Mu nu are matrix indices, mu rows and nu columns. You will make these components, instead of real numbers, you will make them matrices. So instead of 4 space-time directions, t hat, I hat, j hat, k hat, I have 8 octonionic directions, here written E1, E2, up to E7. 7 are non-commuting, 8th is ordinary. So this matrix, which describes the dynamics variables now, this matrix has 8 matrix valued components. Here the components are real numbers. Here the components are real numbers. Here the components are matrices. So a matrix divided into other matrices, one matrix per direction, and 8 of them. So this is a matrix valued vector. So instead of Q here, I will have capital Q. There are reasons why they have to be Q1 and Q2 separate. So this is my action principle in the cloud. There are only 3 fundamental constants: Planck length, Planck time, and h bar. That's it. Everything else now has to be derived. That's the goal. Instead of mass, I have written a unit 1 by length. That is doesn't matter. LP square by L square. This was like Q dot square. I have replaced it by Q1 dot dagger, Q2 dot. Dagger is what defines the adjoint. And now this is a matrix. I cannot have my action as a matrix. Action is a number, it's a scalar. So I take the trace of the matrix. So compare this, instead of a free particle like this, I have a free particle like this. So this is how I would describe an electron in the cloud as opposed to the terrain. There's only one free parameter associated with the electron, which is this length parameter L. This entity is what I call an atom of space-time matter. There is no distinction between space-time and matter. And you should ask, oh, what is this time? Because you have given up time, you want a formulation without classical time. It turns out when we work with these non-commuting spaces like octonions, we are in the domain of non-commutative geometry, and for some profound reasons, non-commutative geometry gives rise to a new notion of time, which is you can call non-commutative time or Cohn's time after the person who found it. This is Cohn's time. So if I have lost classical time, but nature has very kindly given us another time, what Cohn's called God-given time parameter. So you are still able to describe evolution in the cloud. In the cloud, there is no classical space-time, but there is a time parameter which allows you to describe evolution. The universe is made up in the cloud as a collection, enormous collection of STM, space-time matter atoms. The STM stands for space-time matter. So there will be one action for every cloud, every atom of STM atom. How many STM atoms are there in the universe? I don't know. At least 10 to the power 80, maybe infinite. We just need them to be a very large number. So the cloud has a mathematical description. Notice that there is no distinction between space-time and matter yet. As I said, I must propose a symmetry principle, symmetry group. Here it was the Lorentz group, Lorentz symmetry. It turns out that if we work with this group called E8 cross E8, it gives us a theory of unification of all the forces. So you get some idea, I hope, as to how I construct the cloud given the terrain by going from real numbers to octonions and from real numbered variables, dynamical variables Q to matrix valued variables. So because we work with the trace of matrices, This is called trace dynamics. So you can vary the action and get equations of motion. So this is like doing Newton's work, doing Newton's mechanics, but with matrices and on octonions instead of ordinary spacetime. That is what trace dynamics is. It turns out this is a theory of unification of forces. How do we understand that? So we are now in the cloud. We are here. We have constructed an exact formulation of quantum mechanics here. We must explain how we recover the terrain from here. Because terrain is what we observe. This we don't observe. We haven't yet seen this in the lab. From here can we come to ordinary world that we see? So this is string theory also starts from something like a cloud. Then they do compactification of 6 out of the 10 dimensions, and they try to reproduce the terrain, but they land up with 10 to the power 500 possibilities, and it is not clear whether our universe is even contained in that. Like Professor Linde said, we have not yet found it. So what we have done, we have a theory in the cloud, and we have a proposal for coming to the terrain, which reproduces the observed universe. No compactification. We are not in 10 dimensions. We are in 8 octonionic dimensions. String theory has 10 space-time dimensions, 9 space, 1 time. No, we have 8 octonionic dimensions plus Cohn's time, which describes evolution. And from there, without compactification, we recover the terrain. So what happens? So in the cloud, what we have is what I call the pre-space-time, pre-quantum universe, which undergoes an expansion, some kind of an inflationary expansion, until the electroweak scale. So the cloud, presumably the universe began as a cloud at the Big Bang scale, underwent some expansion. That part is we are still developing. Up to the electroweak energy scale of 1 TeV, when a symmetry breaking takes place in the following manner. We have E8 cross E8 groups. Both the E8 groups undergo a branching and symmetry breaking. I am short of time. Just to say in brief that when you do this kind of a symmetry breaking, what emerges is the classical spacetime of the terrain. At the electroweak scale, because of such a symmetry breaking, we get classical spacetime in the terrain along with the 4 known forces: strong force, weak force, electromagnetism, gravitation, and one new predicted force, which we have called dark electromagnetism. So when symmetry breaking happens, the octonions are replaced by real numbers. That's the quantum to classical transition. That is how space-time is recovered without doing any compactification. So octonion has 8 directions. 4 of them become space-time directions. The other 4 become internal symmetry directions, in which the strong force, the weak force, and the electromagnetic force live. And we didn't have to do anything by hand. How to get 4? It comes out naturally that way. There's a reason why space-time emerges as 4-dimensional. Then those STM atoms which do not take part in the quantum to classical transition, they stay quantum in nature. They stay in the cloud, but I can also describe them using the terrain. So now the technical part is over. How much time do I have?
5 more minutes to conclude, sir.
Okay, so I can go fast now because the technical part is over. So we have a formulation of quantum theory without classical time. We have a unification theory, E8 cross E8 unification. What do we learn from it? If you work in the cloud, you have much more information than in the terrain. The cloud is a more precise description even at low energies. An example is a macroscopic solid. If you take a stone, you just know its surface. You don't know that there are atoms inside. But today physicists know that the properties of the stone are determined by the atoms inside. So atoms and the macroscopic solid. The terrain analogy is the macroscopic solid, and the cloud are like the atoms. That's why I call them atoms of space-time. So I took this screenshot of Professor Linde's slide the other day because I liked it very much. So I'm reproducing it. Let's read it again. I would like to state a theorem, Einstein says, which at present cannot be based upon anything more than a faith in the simplicity, intelligibility of nature. There are no arbitrary constants, that is to say, nature is so constituted that it is possible logically to lay down such strongly determined laws that within these laws only rationally completely determined constants occur. My claim is that we have arrived at that stage. From Einstein said this in 1949, and although Professor Linde said that this dream is not fulfilled because of the multiverse, I am claiming that this dream is being fulfilled because we work with the octonions. The octonion structure is so rigid that if we make space-time with octonions, space-time tells matter what to be. So we say in gravitation, matter curves space-time, space-time tells matter how to move. Now space-time not only tells matter how to move, it also tells matter what to be. That is why are there electrons, neutrinos and quarks? Why only those particles? Why 3 fermion generations? Why do they have those particular values for masses? We are now able to start being able to answer these questions. And I give you one example which we are quite happy about in our work. And that is the masses of elementary particles leaving out neutrinos. These masses take very strange values. Have a look here. Electron, up quark, down quark, strange quark. Look at these numbers. They don't show any obvious pattern. And I can make it easier for you to visualize. These are the elementary particles, quarks, electron family, down quark family, up quark family, and the neutrino family. There are 4 families and there are 3 generations. And what are the charge ratios? Neutrino is uncharged, electrically uncharged. The down quark charge is 1/3 that of the electron. The up quark charge is 2/3 that of the electron. Within a family, all the 3 particles have the same electric charge. The electron, muon, and tau lepton have the same charge. Similarly, down strain and bottom have same charge, etc. But look at the masses, how the mass changes. 4, these are mass ratios. If the electron is 1, the top quark is 3,40,000, 8,180 for bottom quark, 207 for the muon. Where are these numbers coming from? We discovered in our work in the cloud with the octonions that we can actually prove from first principles that the observed masses are actually nothing but these following ratios which are derived from theory. Suppose I set the down quark to 1, then the electron is 1/3, the up quark is 2/3. Strange quark is this number. Notice this very pretty square root 3/8 which comes everywhere. And then other than that it is 1, 1/3, 2/3. And I can write, you can see this paper, and I can write this in a simpler way in this table. If you define delta as this number square root 3/8, these 3, 4, 5, 6, 7, 8 numbers define all the funny numbers that you see. And we work with square root. The square root mass ratios, up quark with respect to the electron is 2, down quark with electron is 3. Similarly, like tau lepton to the muon. These are theoretically derived fractions where delta is square root 3/8. You put in the value of delta, this is the number in decimals. Like I take this number, delta root 3/8, decimal value is this. And this is the experimental value. So we agree to within few percent or few tens of percents. Here there is a bigger disagreement. 3, 2.34, 2, 1.59, 4.15, 4.46, 6.7 here, 4.15, 4.11, 14.09, 14.23. So there is not perfect agreement, but the so-called mass hierarchy is reproduced. Like, the top quark was 3,40,000 times the electron. That is explained by these ratios, which, as I said, are derived from theory. Okay, now to the last part of the talk. I'll finish in 5 minutes. What are the possible implications for cosmology? Before the electroweak symmetry breaking, the universe is a collection of enormously many atoms of space-time matter. There is no distinction between matter and space-time. No distinction between the physical. Yes, I forgot to emphasize this. There is not only is it that matter and space-time are indistinguishable, I cannot distinguish the physical world from its description by mathematics. What is the definition of an atom of space-time matter? It is defined by this action. That's all I can say. I cannot say hold a STM atom in my hand because there is no space-time. So what is meant by holding? This is it. This is the fundamental entity of physical universe from which everything is made, and it is described by this mathematics. So I say that at the most fundamental level, there is no distinction between the physical world and the mathematics it describes it. So where does mathematics live? I don't know, but perhaps mathematics is equal to physics, and that is the cloud. Why is the cloud there? I don't know. But at least we can say, why is the universe there? I think because there is mathematics. Why is there mathematics? I don't know. So now, was the Big Bang a spontaneous collapse in a sea of STM atoms? So so this is the fundamental state of the universe. It's a collection of mathematical collection of STM atoms, which I have shown with like these balls, but of course they are not localized. There is no space-time here. Maybe some dynamics is happening in these STM atoms, some entanglement, some spontaneous fluctuation where lots of STM atoms come together and collapse to form what we call a universe. Let me make it a little better. Imagine, this is the analogy. Imagine gas molecules in a box undergoing a rare fluctuation. So these are like my STM atoms. They have been going around, the gas molecules are going around in the box. Every once in a rare while, extremely rare, there will be fluctuations such that the whole gas will come in one corner of the box. What will happen after that? Then it will start spreading out. So my claim is that perhaps, I don't know how to prove it, that from these STM atoms, if there is a spontaneous localization, after that what happens is the Big Bang and the expansion. So this is our universe is created as the opposite of spontaneous localization. So I actually in the last few months I'm interacting very heavily with AI like ChatGPT Pro and Anthropic's Claude. They are really becoming very useful and important for research. So I asked this question to Claude. Given all molecules in one corner of the box, maybe because there was a large spontaneous fluctuation, so spontaneous fluctuations send the molecules to a corner of the box. What will happen next? Will it be like the Big Bang, an explosion, expansion into the whole box, proceeding towards homogeneity? Okay, so this is the answer. See how well is AI thinking these days. What a beautiful analogy. Yes, exactly. A large language model is saying things like this. This is the answer from Claude. A spontaneous fluctuation concentrates everything into a corner, and then the system expands outward towards equilibrium, just like the universe after the Big Bang expanding towards homogeneity. So in detail, yes, this is exactly like the Big Bang in miniature. The molecule, this is again Claude saying. The analogy to cosmology is striking. In your octonionic theory, The universe begins in a collection of enormously many STM atoms in a unified E8 cross E8 phase, the analog of all the molecules packed in one corner. Inflationary expansion then drives these atoms outwards, and when critical entanglement triggers spontaneous localization at the electroweak scale, classical spacetime crystallizes out. The analog of the gas reaching thermal equilibrium and filling the box uniformly. The sequence of our four pictures tells exactly this story: uniform equilibrium, corner localization, expansion, and approach to new equilibrium, etc. So, maybe there are multiverses in the following sense. Underlying its substrate is a mathematical collection of STM atoms. Spontaneous localization is happening all over. In infinite, I don't know. What even infinite means, there's no space-time here. So universes are perhaps being born all the time. All the time means Cohn's time, non-commutative geometry time. And within the universe, then electroweak symmetry breaking happens. It forms stars and galaxies. Those stars and galaxies will eventually all become black holes. Black holes will evaporate by Hawking radiation, which is quantum. Once everything is quantum, you are back to STM atoms. So maybe, like in the Indian philosophy sense, universes are being born and dying all the time. Here is our universe, we are here. Once it, far long in the future, after hundreds of billions of years, it will again evaporate into Hawking radiation via black hole. It will go back to this state. It will go back to the STM atom state. And then again, the difference from Professor Linde's case is this is like a multiverse, but the laws of physics are the same everywhere. The fine structured constant is always 1 by 137. There are always only four fundamental forces. This is where I differ from him and from string theory. I agree with Einstein. The universe is rigidly determined to be what it is, except that we may have multiverses. So nothing wrong with multiverses, but laws of physics are universal. And this is my last slide, summary and outlook. There must exist at all energies a reformulation of quantum theory which does not depend on classical time. We have developed such a reformulation by using the laws of trace dynamics, non-commutative geometry, and replacing points by octonions. This is a pre-spacetime, pre-quantum theory. The fundamental entities of structure are atoms of spacetime matter. They obey a simple action principle based on matrices. The assumed symmetry group is E8 cross E8. We have a candidate theory of unification, which is an alternative to string theory. I invite you to ask ChatGPT to compare my E8 cross E8 octonion theory with string theory and say which is better in which way. I tested that. So it's a very long 10-page answer that ChatGPT Pro gave, saying in what way my work is less developed than string theory and in what way it is more developed. Our biggest strength is we have predictability, falsifiability. We predict things that can be tested by experiment, and we don't have 10 to the power 500 vacua. We have only one vacua, that is the observed universe that we see. Symmetry breaking at the electroweak scale gives rise to the observed spacetime and observed fundamental universe forces. We are able to derive values of some of the fundamental constants like mass ratios. This is ongoing work. The ambition is that every fundamental constant will follow from the octonionic picture. More work remains to be done to understand how we go from the cloud to the terrain, why neutrino masses arise, what is dark matter, and lab tests of the predictions that we have made. I'll stop here. Sorry for overshooting my time. Thank you for your attention.
Thank you, sir. Thank you. Thank you very much. Yeah. Without further wasting much time, maybe we can take questions. So, yeah, once again, to remind all the audience, please scan the given QR code to send your questions. And also do use the link, Google form link that is provided over the chat. Yes, can we have first question, please? This is from Bak from Bangalore University, India. He is asking, sir, please explain how symmetry breaking occurs from the cloud to terrain.
Yeah, very good question. I did not go into some enough details. The symmetry breaking is actually a transition from quantum to classical. So it is like the Higgs mechanism, but for a reason. I have to make one assumption that the universe has 10 to the power 80 STM atoms, observed universe. If I make that one assumption, if I take that one number from observed universe, 10 to the 80, then I can argue that when the universe cools down to a TeV scale, a quantum to classical transition takes place precisely around the TeV. This I can derive if I take n as 10 to the 80. And that is where the symmetry breaking happens. So the symmetry breaking is a quantum to classical transition. That is the best way to look at it. And then the branching that I showed, SU3 cross SU3 cross SU3 cross SU3, is one possible branching which I can argue is favored for on certain mathematical grounds. I don't know if I answered your question. The symmetry breaking is a quantum to classical transition which takes us from the cloud to the terrain, and it is essentially the Higgs mechanism of particle physics. But there is a second Higgs, there are two Higgs bosons involved. So we predict that there is one new Higgs boson which should be looked for in the laboratory. If it is not clear, please email me. I try to answer your question better.
Wonderful, sir. Thank you. Maybe it will help him. Yeah, can we have next question quickly, please? Yes, this is from Harishankar Nath Tiwari from University of Petroleum and Energy Studies, Dehradun, India. Sir, if space, time, and matter emerge from the cloud level, is it theoretically possible to engineer correlations at that level that effectively bypass classical distance?
Thank you. Very nice question. Very nice question. You are absolutely right. In the cloud, indeed, there is no classical distance. There is no notion of space-time and classical distance. You are absolutely right. And there are, so you can call quantum correlations, as you said, but there is no distance. True.
Yes. Thank you, sir. Thank you. Next question is from Jagdishwar.
Yes.
Why the time 10 power minus 12 seconds is always mentioned? How we get the value? Can you please elaborate?
Yeah, thank you. Very nice question. So we have made one assumption that the universe began at the Big Bang, not infinite energy, but Planck energy, 10 to the power 19 GeV at Planck time, just 10 to the minus 43 seconds. So this is the starting assumption, 10 to the 19 GeV at 10 to the minus 43 seconds. Then as the universe expands, it cools. The energy, the average energy comes down. And there is a scaling law, which I have assumed, I must say, I must confess, your question is good. In cosmology, there is a standard scaling law, which I assume, that the average energy falls as square root of time. Yeah? E goes as t to the half, square root t. So energy has to come down from 10 to the 19 GeV to TeV, which is 10 to the 3 GeV. Energy has to come down by 16 orders of magnitude, which means time has to come down by 32 order of magnitude because E is going as square root t. So 10 to the minus 43 and 32 orders of magnitude, that is 10 to the minus 11. So minus 11, minus 12, roughly. So I hope you get the picture. There's an energy time relation. E goes as square root t. As the universe cools, I come down from Planck energy to TeV. I know how much time I will have passed by in that much. I hope you get the idea. Again, otherwise, please write to me.
Yes, sir. Can we have one last question? Yes, sir. This question is from Pradeep Kumar, Kendriya Vidyalaya, Sangathan, India. Thank you for your insightful explanation, sir. I would like to humbly ask, quantum mechanics explains the behavior of particles at the atomic and molecular level very well. And the small components seem to continuously build up into large structures like planets and galaxies. However, quantum theory does not fully explain large-scale phenomena, while great general relativity does not describe quantum behavior at very small scales. What kind of theory or understanding can bridge the gap between quantum mechanics and general relativity? I hope this is first part of the question, and one more follow-up question is there. It is like, so would you like to answer this question first,
Yeah,
sir?
yeah,
Or,
let us do this first. Good. So the theory that I have developed is answering precisely your question, which is the theory which bridges the gap between quantum mechanics and general relativity. It is this exact formulation of quantum mechanics in the cloud. So in the cloud, we have atoms of space-time matter, we have octonionic space, we have trace dynamics for matrix valued degrees of freedom. We know how these atoms of space-time evolve. So what the cloud theory is the gap, it does bridge the gap between quantum mechanics and general relativity. So that's precisely what we are doing. Also, second question, how should we understand the collapse of the wave function? What really happens during this process? Is it possible that our current theoretical framework is incomplete, or could hidden variables be involved? Yeah, very good. So trace dynamics, the octonionic theory in the cloud, actually also explains collapse of the wave function. As you rightly pointed out, quantum mechanics has the quantum measurement problem. It cannot explain collapse of the wave function because the Schrodinger equation is nonlinear. The collapse process, Schrodinger equation is linear. The collapse process is nonlinear. It breaks linear superposition. So we need to modify quantum mechanics in order to explain collapse, and the octonionic theory in the cloud turns out to be the right kind of modification which explains collapse. What happens really? This is related to also what are known as objective collapse models, or the Ghirardi-Rimini-Weber theory of collapse. The Schrodinger equation gets modified to have an imaginary part in the Hamiltonian. That imaginary part is also nonlinear. A nonlinear imaginary correction to the Schrodinger equation, which we don't put by hand, it comes out of the theory. A nonlinear imaginary part in the Hamiltonian breaks superposition. So the breaking of superposition is very negligible for small systems like electrons, but it becomes very significant for large objects like tables, chairs, and planets. So collapse happens very rapidly for large objects in this theory. So I should say that this Ghirardi-Rimini-Weber theory of collapse is not yet confirmed in the lab. Every experiment still agrees with quantum mechanics. To explain collapse of the wave function, we need to modify quantum mechanics, but such modifications are, as of now, only in theory. They have not been detected in the lab, though people are looking for these modifications. So, in real truth is that the collapse of the wave function continues to be an unsolved problem. The octonionic theory that I described is one way to solve the collapse problem. Again, this is there in my papers, which you can find on my TIFR website, or please write to me if you want more details and references. Thank you.
Thank you, sir. So we encourage all the participants to write to sir if you have any further questions, and maybe our technical team can also forward the questions that we received. Sir, we do have more questions, but because of shortage of time, so we would like to conclude here. And I also request the participants to do bear with us for 5 more minutes. We are going to conclude. Before concluding, we do have 2 or 3 announcements to make. Sir, thank you actually for bringing up new concept which is giving hope for our understanding. So maybe it will help us, mostly the physicists, to explore and come up with a unified theory as you are proposing. Maybe I hope it will one day give us, or at least bridge the gap to some extent. So thank you for your wonderful insight, and thank you for joining us. So on behalf of Bhaktivedanta Institute and all the audience that are present here, we would like to sincerely thank you for your new proposal of this new concept, and this I think our audience has gained very much. Maybe few questions may come to you, I think.
Yeah, sure. I'll be happy to interact with the participants. They can write to me. Thank you very much for listening. I enjoyed talking to you.
Thank you, sir. Thank you. Thank you. We hope to see you more frequently so that we can learn more from you. So with this, we are almost completing today's session. Before closing, we have a few announcements to make, as I mentioned. So today we have witnessed 3 wonderful talks by eminent professors, which has enhanced our knowledge band and also raised few more questions in order to explore further, understand further about the cosmology at quantum level as well. So we hope we will continue the enthusiasm till the finish of this lecture series. Tomorrow we'll have an interesting lineup of lectures which are shown on the screen, starting with A Fortunate Universe, Life in a Finely Tuned Cosmos by Luke Barnes from Western Sydney University, Australia, followed by a lecture titled Does Universe Have a Purpose by Sri Vasudev Raji, President Bhaktivedanta Institute, alumnus of IIT Kanpur. And tomorrow session will be concluded with a talk titled The Universe, Its Beginning, Its End, and the Role of Humanity in Universal History by Frank J. Tipler, Professor of Mathematics, Tulane University, United States. So I would like to bring to your kind notice about our interesting publications, which are very much recommended for this guest audience that are present here, who are trying to know about the cosmology. So we do have this 2 volumes of Savijnanam volume 11, which is the mathematics of universal beauty, which unlocks the mathematical elegance of the universe. So renowned astrophysicist Professor Mario Livio guides readers through the golden ratio, revealing how this divine proportion dictates the structures of galaxies and the very fabric of reality. It is an essential read for those seeking to bridge the gap between science and symmetry. So please do visit our website store.binstitute.org, where you can find all these publications. And yeah, we have one more interesting volume of Savijnanam again, the astrobiology of our origins, in volume 10. So it delves into the profound mysteries of the deep cosmos with volume 10 of Savijnanam. This edition features a centerpiece article by the world-renowned astrobiologist Professor Chandra Wickramasinghe, explores his groundbreaking research on cometary panspermia theory, challenging our fundamental understanding of how life has begun on Earth and its ancient ancestral connection to the stars. So again, please do visit our website store.binstitute.org So these are very interesting, and this theory by Vikram Singh, actually, it is a new proposal which is in contrast, or which is proposing other concept like life has come from an extraterrestrial space. So it will be very interesting article. So please go through it. And once again, I would like to remind you the timings of the lectures are 5 p.m. to 8 p.m. from Monday to Friday, which is concluding, which is finishing tomorrow at 8 p.m. And day after tomorrow, the session is from morning, according to Indian Standard Time, 10 a.m. to 1 p.m. So please do look about the change in time. So day after tomorrow, you need to join from 10 a.m. morning. And tomorrow, as usual, you have to join from 5 p.m. The session will go till 8, possibly. So with this, we have come to an end for today's session. So we would like to thank all the participants, all the speakers, dignitaries, and guests who have patiently with us till the conclusion of the session. And thank you all for joining today. Looking forward to seeing you all in tomorrow's session and further coming sessions. Thank you very much.